感觉，全世界为我鼓掌啊。
Okay, hello everyone, all over the world, from all over the world. This is Miss Kim from Sungkyunkwan University in Korea. I'm very honored to welcome everybody here. This is a very special event, iCANX Young Scientist Award Final Defense. So I'm so excited to hear a very amazing presentation today. So I'm the moderator, and here's my co-moderator, Professor Martin Teo from Iowa State University.
Thank
so
you,
Martin,
Miso.
would you want to say hello?
Hi, everyone. Thank you, Miso, for the introduction. I want to introduce our committees, both at the finalist selection. The finalist selection was done by this committee here. Of course, Professor Aris Haixie Zhang, Professor Paul Weiss, Yuri Gogotsi, Ran Fu, and Eugen Brugger. And then today we will have the final awardee selection committee, which will be Professor Aris, Professor Paul, Professor Nick from MIT, Professor Chris from University of Twenty, and Professor Zhengui from University of Electronic Science and Technology of China, and that will be on top of the two moderators. Next slide, please.
Okay, so we have these amazing sponsors this year. So the Young Scientist Award sponsors, we have 5 of them: Applied Physics Reviews and Light Science and Applications. And of course, we have ACS Nano, and then Nano Letters and Soft Science. And thank you very much for our sponsors. And would you like to? Okay, so this year we have amazing 47 candidates from 15 countries. It's very impressive. And among them, we had a hard time to select 21, and you're gonna see the final 21 here in the next page.
So these are our finalists. So we will have all 12 of them today, and then tomorrow we'll have 9. And then we will then have the award ceremony. So for today, these are the candidates who will be presenting. And then for tomorrow, we will finish with these 9. And the selection was done by the candidates themselves. The order was determined by them, not us, during a draw. And we appreciate everybody's presence here. And welcome to the Young Scientist Award Final Defense. For today, we have number 1 to 12. Candidate number 1 is Xin Qian from Huzhong University of Science and Technology in China. They'll be talking about harvesting low-grade heat with ions. Xin?
Yeah, can I share my screen now?
Okay. Yes, please.
Sure. Does it come over? Hello, can you see the screen?
It's coming.
It's still coming?
Yep.
Okay.
No, it's very slow.
You can,
We don't know why.
See it. Yeah.
Chen, you can share one more time. Yeah, now we couldn't see you.
Xin, please share your slide. Okay, we can see them now.
Okay, looks good. So Xin, would you please turn on your microphone as well?
Okay. Share. Okay, now it's good, right?
Yep.
Okay. Hello, everyone. My name is Jingchen. I'm very glad I'm be the first one to talk about this research. So the topic today is harvesting low-grade heat with ions. Let me start my talk introducing to you the potentials of harvesting low-grade heat, and hopefully I can convince you that ions are very promising energy carriers for this. So this figure actually shows the energy consumption of the United States in 2020 And you can actually see that majority of the energy ends up rejected into the environment, and primarily in the form of heat. Waste heat actually have a wide temperature distribution, but the majority of the waste heat, 63% worldwide, is the so-called low-grade heat with temperatures lower than 100 degrees Celsius. So if we can actually harvest this huge amount of heat, it will be a very promising step towards the carbon neutralization and slow down global warming. In addition to the industrial low-grade heat, our body is also a low-grade heat source. Due to the temperature difference between the body and the ambient, we are constantly dissipating 3 to 5 watts of energy into the surroundings. And if we are able to harvest them, we can achieve self-sustained sensors, right, without ever exchanging the batteries. So especially during this pandemic time, we can actually harvest the respiration rates, blood oxygen, monitoring the blood oxygen and temperatures of the patients without ever getting in contact with the patient. So that would actually cut off the chances of getting infected. So basically, these are the dreams we have, making use of low-grade heat, but harvesting them has been a long-standing challenge. So to do so, you actually need to build a heat engine. And the conventional way to do so is using the organic Rankine cycles. So the organic Rankine cycle is similar to the Rankine cycle, which is essentially the working principle of a fire power plant. We basically boil the water. But organic Rankine cycle is using organic liquid with low boiling point. But as you can see from here, that this device is pretty bulky with a lot of expanders and pressurizers, which requiring heavy maintenance. As a result, it's not really economically feasible for harvesting low-grade heat with temperatures lower than 100 degrees Celsius. So an alternative way to do so is called the thermoelectric devices. These are all solid state. So basically, thermoelectrics is relying on the drift of electrons and holes from the hot side to the cold side. But the problem for thermoelectrics is that the thermal voltage is very small. With 1 degree of temperature difference, you're only able to generate 0.1 millivolt of voltage. So that will make it very difficult to achieve the voltage requirements of a lot of micro devices. So considering if you're making use of a low-grade heat source, 50 degrees higher than ambient, you will need 200 of such TELECs to achieve a voltage of 2 volts. And that would be very expensive, considering these thermoelectric materials contains heavy and rare elements. So do we have a better option? And recent years, people find out that ionic electrolytes, it would be a promising energy carrier for harvesting low-grade heat. For example, ions can also go through thermal diffusion from the hot side to the cold side. And researchers have found that if you can confine these ions in very thin nano channels, you can actually achieve a very high thermal power. Ions can not only go through transport process like thermal diffusion, they can also react. So a different mechanism other than the ionic seeback effect is called the thermogalvanic effect. So basically, when you have a pair of ions that can react with each other, and you maintain the electrode at different temperature, that can also give you several millivolts per Kelvin of thermal voltage to harvest low-grade heat. And comparing with thermoelectric materials, ionic electrolytes are very cheap and easy to synthesize. Now, looking at these two mechanisms, both of them are driven by temperature gradients. So a fair question to ask is that, can we combine them to further boost the thermal power and device performance? So the answer is actually yes. In this slide, I will introduce you to the so-called synergistic effect between thermal diffusion and the redox reaction. So for thermal diffusion, what really happens is that the ions is driven by the temperature gradient, migrating from hot side to the cold side. So when you have a temperature difference, you generate a concentration profile, and the proportionality is called the Sorel coefficient. When the Sorel coefficient is mismatched for cations and anions, you're going to accumulate opposite charges on the both electrodes, and that will induce an electric field across the device, which gives you a thermal voltage. So this is so-called the ionic feedback. Now let's actually look at this redox reaction. So redox reaction is a bit different. It only happens at the interface between the electrode and the electrolyte. And it turns out that the thermal voltage is actually determined by the entropy change of the redox reaction. In this figure, we basically use the example of ferrocyanide with 3- charge, which is the high entropy state, and ferrocyanide ion with 4- charge, which is the lower entropy state. So when temperature rises, the entropy favors the production of higher entropy state. So on the hot side, we will have oxidation, but on the cold side, the opposite reaction actually happens. That this chemical reaction shift also generates a voltage. So when these two voltages are in the same direction, you can actually achieve a boost when the electrolyte contains both redox pairs and ion providers for thermal diffusion. So with this actually physical picture in mind, we developed a ionic jello. Basically, we make a jello contains ion providers, which is KCl, potassium chloride, and ferrocyanide as the redox couple. So to make it gelatin, we fabricated we make the electrolyte quasi-solid state, so that we are free of encapsulation issues. In this material, we actually achieve a record high thermal power in the quasi-solid state electrolyte, which is 17 millivolts per Kelvin. And that is 10 times larger than the aqueous solution of ferrocyanide, 100-fold larger than most of the semiconductors. And we also fabricate a glove containing 25 of these ionic thermoelectric modules in series. And using skin temperature, we achieve a high voltage of 2.2 volts. And compared with the other semiconductors, our voltage is higher, but using much smaller amount of ionic thermoelectric modules. So this work actually provides a strategy for boost thermal power and to harvest the small temperature difference between the body heat and the environment. We also do charge and discharge tests of hundreds of rounds, and we basically do not observe obvious performance decay. But there are remaining challenges. One is that the power decays with time, and that is because the thermal diffusion is a physical effect. So the current is capacitive. Also, this method, while it's very good for wearable devices, it's not easily scalable, especially when the heat sink and the heat source is far away. So the question is, do we have a continuous method which can generate steady state power and which is also scalable so that we can harvest low-grade heat from industry? To do that, we actually look into a different mechanism, which is called a thermally regenerated electrochemical cycle. And the working principle is basically the voltage of a battery also depends on temperature. So for example, in this battery, the voltage rises with temperature. So we discharge the cell at higher temperature when the voltage is higher. After that, we cool the cell down and the voltage is lower, and then we do the charge. Through this cycling, we can actually achieve, harvest some amount of network. But still, with a single cell, the power generation is still not continuous. To solve this problem, instead of using a single cell, we can use two cells, two flow cells actually, one at high temperature, the other at low temperature. The redox reaction happens in the opposite direction, and we circulate the electrolytes. In doing so, we can achieve continuous power generation. So this idea is actually first proposed by Professor Majanda's group. But previous work, the most challenging issue is the stable operation. In previous work, they used the vanadium electrolyte versus the ferrocyanide. But the vanadium side is very acidic, but the other side is neutral. So under operation, there will be protons exchange from the vanadium side to the ferrocyanide side. And that will actually induce a degradation here, which is, and also production of toxic species like here. So basically this cell will fail several hours. To solve this problem, we actually replace this vanadium, which we actually screen a lot of electrolyte. We replace the vanadium to the potassium iodide and triiodide. Instead of proton exchange, we do potassium ion exchange. And in doing so, both electrolytes are actually pH neutral. We don't have to worry about acidic induced corrosion problem. And this cell can actually stably operate without the degradation. So as you can see, we do discharge tests. When the temperature rises, we can generate the voltage. We can also achieve steady state power. So in this work, using the pH neutral flow battery, continuous power generation with low-grade heat is achieved for the first time. Future improvements are still to be done, especially when considering power density, right? So we actually do some analysis and find out that the mass transfer loss is the major mechanism of power loss. The reason is that we need to supply the reactants from the bulk solution to the interface. Until then, basically, we can do the charge transfer between the electrode and the electrolyte. So if the mass transfer process is slow, you will have a degraded power. So in the next step, we are going to try to look into the ways to design really hierarchical porous structure of the electrolyte to really enhance the mass transfer. So after solving this issue, another point I would like to emphasize here is that this method, not only can it operate stably, it's also have the potential for scaling up, right? For example, if we have a larger amount of low-grade heat, we can basically stack the cells together. We can scale up the power for low-grade heat harvesting. So with that, I can give the summary here. Hopefully, I convinced you that ions are very promising energy carriers for harvesting low-grade heat. So in the first part, we provide actually a strategy for achieving giant thermal power electrolytes. By combining the thermal diffusion and the redox reactions, we achieve the synergistic effect and a record high thermal power in these electrolytes. We also developed a pH neutral thermally regenerative flow battery in the second part, which allows for continuous power generation using low-grade heat with the potential for scalability. So with that, that's all my talk. And thank you for your attention and any questions.
Any questions? Thank you very much. That was perfect timing. Appreciate it.
Thank you.
Question, I can ask you one very quickly. In your exchange from using a proton shuttling to a potassium shuttling, right?
Right.
Potassium is heavier than hydrogen, than the
That's
proton.
true.
How is that going to be energy efficient?
Yeah, that's a pretty good question. We actually analyze this in this sort of modeling. We do find out that majority of the internal resistance comes from the membrane. So I would say in the future, which is also mass transfer process. So if we were able to develop a better membrane, especially for alkaline metal ions instead of protons, we can also achieve. We can also improve the power density.
Right. Mm-hmm. Thank you.
Okay. Yeah, I have another question. So basically, if you look at those semiconductor thermoelectric devices, you can run it backwards to use it as, for example, Peltier coolers or heaters.
That's true.
Does these ion-based devices have the same capability? Can we run it backwards to achieve heating and cooling by converting electrical energy back into temperature difference?
Yes, we can. And that's actually my ongoing research. Basically, when you supply power to it, right, you can revert the thermodynamic cycle. And through this entropy change, you can also achieve refrigeration. And that's actually my ongoing research. Yeah.
Okay, thanks.
Thank you.
Next candidate. Thank you very much.
Thank you. I can stop sharing now.
Yep. Miso, I hand over to you.
Okay, so it's my great pleasure to introduce our second speaker, Professor Jingchen Yu from Harbin Institute of Technology. And he'll be sharing his research on active targeted delivery using swimming nanorobots. So the stage is yours.
Okay, thank you. Thanks for the opportunity to the final defense. And my name is Zhigang Wu. I'm working on the actively target delivery using the swimming nanorobot. So first, I want to introduce the background. A conventional delivery system like the oral administration or intravitreal injection, they are all relies on the diffusion of therapeutic molecules or cargoes in our bloodstream or other biological fluid. So these passive delivery strategies leave many issues. For example, the low efficiency in our disease area and a really high side effect. And some work that summarized the recent 30 years in the nanomedicine, and they found that so the most of the nanocarriers, so the delivery efficiency at the disease area are below 0.7%. So to solve the problem, so people imagine that someday we can create the nanorobot that can swing our body and actively deliver the drugs or other therapeutic agents to the disease area and to cure the life-threatening sickness. So in this active delivery strategy, so we can they leave the advantage such as high efficiency in the disease area and low side effect. This idea is originated from Professor Richard Freeman in 1959. So besides that, he also wondered someday we can create the tiny machines used by manipulation of individual atoms or molecules. This is currently we call it the bottom-up technology. And in the recent 2 decades, there are a lot of swimming robots have been developed, even for me. So I also developed swimming robots which can be driven by the chemical reaction, the NR light, or magnetic field. So besides this linear motion or random motion, so that we can also control the motion to the target by the manipulation of external field. Well, in my last defense, so Professor asked me, so Zhigang, I know a lot of guys, they are all doing the same things. They can also make the particles make the propulsion in some fluid, right? So what is your exclusive innovation of your research? So I would say, so besides their single propulsion in the pure water, there are a lot of challenges to be solved to realize the active the practical applications, right? For example, the most of swimming robots are made by the MEMS or electrodeposition. They are all made of metals or artificial polymers with poor biodegradability or biocompatibility. And in our previous work, so I would say my innovation is so I'm not working on the mechanical science. I'm working on the chemistry. So I bring the colloid interface technology to elevate the adaptability of swimming robots in vivo. So basically, we know the proportion, we learn from the proportion from the swimming microorganism like sperm or bacteria, that we know their proportion theory. So unlike the polymers or artificial or metals, so we can use biolateral polymers like polysaccharide proteins as building blocks to fabricate the structures. And these structures can be driven by the external magnetic field horizontal chemical reactions. And in our previous work, so we can use this bottom-up controllable assembly. We can fabricate the structures with controllable geometry like helical geometry and nanorod geometry. We can also fabricate them with biodegradable building blocks, such as polysaccharides, proteins, or cell membranes. In this case, so we can have our structures with good biodegradability, and the other case is about combability. You know, if the swing nano robots are made of the metals, they are foreigners. So once they are entering our bodies, our immune system will recognize them as foreigners. Then they will be, before they're doing something, they will be attacked by the immune system. To solve the problem, we wonder that, you know, the natural cell membrane have a lot of biological IDs. So if we can coat this red blood cell membrane on the surface of swinging robot, and they could be camouflaged as the natural cells. In this case, we can activate the immune attraction in the bodies. This is our previous. Well, in today, the other two things is not so exclusive. So today we want to talk about how can we make swing nano robots to propel in the complex biological media. For example, this is a well-known helical swing nano robots in water. I think maybe you know a lot about it. They could be propelled very well in the pure water, but once they are going to the dense tissues or biological fluid, it's not so easy work. For example, once this swimming helical magnetic nano robots are released in the vitreous phase, you can see they cannot make a full rotation, so they cannot make any displacement. Then basically our work can be separated into three parts for the propulsion in complex biological media. The first one is porous media. In our bodies, there are a lot of tissues like the vitreous or the mucus in airway, so they could kind of like a sticky structure. So in the microscope, so they have their own structure. It could sometimes it looks like a hydrogel. They are 3D-dimensional networks, which is using the type 2 collagen as backbone, and the hyaluronic acid and the water are inserted into the network. So how can we make this? How can we make swimming nanorobots penetrate this porous media? For example, we use the vitreous as a research item. So in the conventional ways, if we want to deliver some drugs on the anterior part of us, it could be easy for using the topical delivery. But if we want to deliver something to the posterior part of us, like the retina, it's quite tough because there are a lot of barriers in our eyes. If we want to deliver through the intravitreal injection, so they need to require the drugs to be penetrated through the vitreous. This is quite density complex biological fluid. So a lot of people wondered, can we create some swimming robot? For example, the magnetic helical structure, they can move in our vitreous, and we can in this way control them to the target area in our retina. But most of the work have failed because, as I said, so there are two cases block the propulsion of the swimmers. The first one is because they are biological network. So the size of the network is 520 to 550 nanometers. If the size of particles is bigger than that, so the spatial block will prevent the propulsion of the swimming nanorobot. And the other case is this building blocks made of the type 2 collagen. They are very adhesive. So any particles they are very like to attach to the type 2 collagen fibers. In this case, to solve this problem, so we design a swing nano robot with smaller size than the match size, with small size and slippery surface. So if we can fabricate structure which is smaller than the match size of the network of vitreous, then we coat a slippery surface on the swinging robot. Then probably we can make the propulsion in the vitreous. In this case, so we can fabricate a structure with this magnetic helical structure with height of 390 to 380 to 390 nanometers, smaller than the match size of the vitreous. And the other cases, we coat the surface with a slippery lipid surface. In this case, the adhesion of the surface is dramatically decreased. In this way, we can see it's a bare swimming helical robot in vitreous, so they can make a full rotation. But if we can coat it with slippery surface, so they can make a propulsion in our vitreous. And this is only one propulsion in the vitreous. Then we can also make a large number of slippery robots through the vitreous of eyes. besides this linear motion, we can also control the directions in vitreous by manipulation of external magnetic field. We can also control the velocity, and the velocity, the maximum velocity could be around 10 micrometers per second. And we're not satisfied the proportion in the pure, the vitreous under the microscope. We want to extend it in an entire eye. So we use an entire posing eye as a item and inject our swimming robot in the middle of the eyes, and using the clinical OCT to image the distribution of the swimming robot. We use the macular as our target. Then we found that the most of our swimming robots are located in the macular of the eyes, and the most of swimmers are located with a region of around with a circle with a diameter of 4 milliliters. So this is the velocity, and the precision cannot be compared by the conventional ocular delivery. So in this case, our work is highlighted by the Nature and Science. Particularly, the physical organization recognize our work as the first time that scientists are able to steer the nanorobot through the dead tissue. And the other case is how can we make a swimming robot penetrate through a biological barrier. We wonder that this is quite tough. We wonder that the natural immune cells, such as the neutrophils, they can penetrate the red blood-brain barrier due to their chemotaxis along the inflammatory factors. So we incorporated natural neutrophils into our swimming nanorobots. So we can use the neutrophils to swallow some magnetic particles with drugs. In this case, so this is structure. So in this case, we can control the motion of our neutrophil hybrid robots with magnetic field. Also, we can make it to swim against the blood flow. Besides that, not only single robot swimming, we can also make them to be emergence of swarms with four individual swimmers. In this case, once we are immersed at swarms, so their motion could be increased from around 16 micrometers per second to around 50 micrometers per second. And in this case, once we can, in this way, we can navigate our swimmers into the blood, close to the blood-brain barrier. So the swimming robot can be using their neutrophil capability to penetrate through the blood-brain barrier by the along the inflammation factors from the glyma. This is the observation of penetration to the blood-brain barrier in a ex vivo model. And this is the penetration of the blood-brain barrier in vivo. In this case, if we achieve the active delivery to the glyma, so in this case, we can extend the half survival period to 2 times to 3 times. And in this, so our work is also highlighted by the Science Robotics in a focus article and editorials. And the other case is how to propulsion in the GI tract. And in 2017, so they published a paper in Nature, perspective paper, and they proposed that the imaging and the control of the swimming robots in vivo is a great challenge for the application, practical application. And the other case is Bob Langer also, he wonders, can we create some delivery system that we can achieve the long-term retention in the GI tract? So we combine these two requirements together to fabricate a swimming robots can move in our GI tract. In this case, we first of all, we encapsulate our swimming robot in our capsules, and we can image the locomotion of the swimming robot using the photoacoustic imaging technique. Once they arrive to the target, we can trigger the propulsion of in our GI tract to release the drugs. And in this, so we to prevent the itch from the gastric acid, so we fabricate a micron capsule made of entry polymers to the lifetime for our swimming robot. And we can also, the swimming robot can be driven by the chemical reaction from the magnesium with water, from the repulsion of hydrogen gas bubbles. And we can also image our swimming capsules along the GI tract. And to better image our structure. So
Sorry, one more minute, please.
Yes. So besides this random motion, we can also so to image our swimming robot in our fields. So we wondered, so they have different motions from our tissues. Our tissues have only respiration motion, and our swimming robot have two motions. So in this case, we collaborate with image analysis to extract the signals that is exclusively from our swimming robot. And to the summary, so we use different strategies, structure design, and slippery surface to for the propulsion in the porous media and the neutrophil hybrid techniques to propulsion to penetrate the blood-brain barrier, and photoacoustic imaging technique to achieve the imaging and control in the GI tract. So thanks for advisors. And also I'm selected in MIT Technology Review in China. Many thanks.
Okay, perfect timing. So now is for committee members questions, one or two.
Yeah,
maybe I can start with the first question. Thank you. Well, very impressive talk. You have achieved clearly a lot with these super small, tiny robots. You showed many fantastic examples and applications, but I'm wondering what are still the challenges that lay ahead? Which challenges need to be solved before these nano robots can really change nanomedicine?
I think one of the emerging or headache processing is still the imaging technique. But because the resolution of current techniques is below, is in the millimeter or micrometer size. But our swimming robot is quite small, even the nano size or just micrometer size. And particularly, because it's motion, so it's really hard. It's also required imaging technique to have a really time, the imaging period, very, very soon. And our locomotion is 3D dimension, it's 3D dimension, but it's really hard to make a, real quick time and high resolution and 3D imaging protocol, something like this. I think it's the most important thing.
Thank you.
Okay, I have a quick question. What happens once the drug is delivered? What happens to the robots? Do they just stay inside human body, or what happens to them?
Yes, thank you. Because the swimming wall are made of the natural polymers like polysaccharide proteins that will be degraded in our bodies.
Okay, Nick, yeah, please.
Yes, I'm really impressed of the new delivery and your manufacturing mechanisms. What do you see as the potential say like obstacles, for example, to demonstrate the effectiveness of delivering through, for example, the blood-brain barriers?
Yes, so we have two ways. The first one is so we can use the ultra thin. We have the ultra thin histologies. So we can like our previous image, we can see the distribution of our swimmers in the glymer. This is the first one. The second one, we can cut the different part of the glymer, so we can analyze the drug distribution by the HPLC, and also we can use label the drugs with the fluorescence, so we can also analyze the distribution of the drugs in glymer or other biological tissues.
Okay, very good. Thank you very much. So we can now move on to the next presenter.
Okay, thank you very much.
Thank you. Martin?
Thank you. Yep. Our next speaker is Dogyuan Lei. He's from City University of Hong Kong in China. He's going to be telling us about symmetry broken plasmonic nanocavity for enhanced nonlinear optics.
Thank you, Martin, for your introduction. You can hear me properly, right?
Yep.
Yeah. This is Dogyuan Lei from the City University of Hong Kong. So it's my great pleasure to attend this final defense for the iCANX Young Scientist Award. Today, I would like to share with you a couple of our recent research stories on symmetry broken plasma nanocavities and how we can use these plasma nanocavities to manipulate the linear nonlinear optical response of local metals. So if you have ever visited the so-called St. Paul's Cathedral in London, if you wish to climb 257 steps from the floor, the cathedral floor, you may reach this very famous place, construction, the so-called Whispering Gallery. It's famous because you actually can hear a whisper of your friend standing on the opposite side of you, actually several tens of meters away from you. So this remarkable phenomenon actually comes from the formation of acoustic Whispering Gallery cavity. When the talker's whisper couples to this Whispering Gallery, it can travel for a long time. And then the listener standing several times away from you, from the talker, can still hear this whisper. Now, if you shrink the size of this gallery by say 6 orders of magnitude, we can reach the micrometer size. So this can be used to manipulate the optical waves or electromagnetic waves. And so we now you see that these cavities actually have been used for many devices like lasers, like sensors, and of course, in addition to those Whispering Gallery cavities, you also have photonic crystal cavities. Okay, but if we look at these cavities, we notice that these cavities are actually made of dielectric materials. So they usually have quite high quality factors because of the low loss of dielectric materials. But the problem with these kind of cavities is that their mode volume is quite large because of diffraction limit. So to overcome the problem of this diffraction limit, we can resort to the so-called plasmoid nanocavities. They are made of noble metals. So by exciting the localized surface plasma resonance in those metallic nanoparticles and couple those nanoparticles together, we can form the so-called plasmoid nanocavities with very, very small mode volume. So for example, a typical example is this nanoparticle dimer. Of course, you can also have a larger variation that's particle on film system. So if you compare the mode volumes and quality factors of these dielectric microcavities and plasmoid nanocavities, here I plot, this graph plots the mode volume in the vertical axis, the horizontal axis is the quality factor. You will find that those dielectric microcavities usually have much larger quality factors than the metallic nanocavities. And but their problem is that the mode volume is actually also up to 10 orders of magnitude larger than the plasmoid nanocavities. So the small mode volume associated with this plasmoid nanocavities that it can be used to enhance the light-matter interaction in both the weak coupling stream regime through the so-called Purcell effect, or in the strong coupling stream. And because as long as you can say from these equations, as long as you have a very small mode volume, you can always have a very large Purcell factor or quite large coupling strength in your system. So my research actually based on those plasmoid nanocavities and dielectric microcavities. And the first topic we are looking at in my group is how we can use those plasmoid nanocavities to manipulate the linear and nonlinear response of noble metals. And in the quantum mechanical regime, we also look at how the free electrons in metals will change their response when you reduce the size to sub-nanometers. And we also couple those nanocavities with low-dimensional materials to realize new devices like micro lasers and optical metal surfaces. And finally, we couple those nanocavities with biomolecules to realize biosensors, and also use those for energy conversion and saving. So because of the limited time today, I would like to introduce 2 stories on how to use plasmoid nanocavities to manipulate the second harmonic generation and photoluminescence in those interesting structures. Now, second harmonic generation in metallic structures have been studied for a long time. And the general solution here to enhance the second harmonic generation is actually based on mode matching. For example, in this study, they designed this V-shaped structure coupled with the metal nano rod such that it has a fundamental wavelength resonance in the near infrared range. And then they also have a resonance in the visible range. So if they match the excitation with fundamental excitation wavelengths with this longer wavelengths and the second harmonic generation and so these short wavelengths, they can enhance the second harmonic generation as see from their measurements. So this is what we call spatial and spectral mode matching technique. Actually, in the past few years, we also used a lot. We also use a similar approach that's based on ferroresonance to enhance the second Hammond generation in those coupled plasmon nanostructures. Now, but if you look at their results, you find that their second Hammond generation conversion efficiency here is around 10 to -10, and the second Hammond photo emission rate is on the order of 10 to 6. Please keep in mind these two numbers, because later I will show you that with our new method, we can increase these two numbers by more or less 3 orders of magnitude. So the other problem with the previous study is that their second Hammond generation is actually occurs in the visible range, where, for example, if you look at this dielectric function, here the left axis is the imaginary part of gold. You find that in their second Hammond generation region, the imaginary part is very small, so means that the intrinsic absorption is very small. So then the problem is that how we can achieve enhance the second Hammond generation in the UV range and even the blue range, or even the UV range, where the intrinsic loss of metal is actually significant. And how about the role of symmetry breaking in our structures? So for this purpose, we have analyzed our plasmon nanocavities. The first structure is a symmetrical nanoparticle dimer. So if you look at this structure and look at the fundamental field response, of course, you can have very large near field enhancement in the gap region. But if you look at the second order response, you will find that the second Hammond dipoles in this structure actually are anti-parallel to each other. So they will cancel out in the near field regime and give you very weak second Hammond generation. But the good thing we found out here that if you increase the dimension of the second nanosphere, for example, the bottom one, and then you will find that the second Hammond dipoles now are not totally canceled. You will have a certain amount of second Hammond radiation from this structure due to the symmetry breaking. And if you reach the extreme case, means that you replace the second nanosphere with a flat metal film, you will find that the second Hammond dipoles now are aligned in phase with each other. So this means that we can get a very, very efficient second Hammond generation. Actually, this symmetry breaking concept has been verified in our analytical calculations. So if you look at the first order response, you will see that these 3 structures show more or less the same near field enhancement. But now if you look at the second order response, you will find that the second Hammond generation, second order polarization field in the symmetry broken particle on film system is much larger than the symmetrical structure. Actually, in the symmetrical structure, you have opposite second order polarization fields. You will cancel out. So to summarize our argument, now we put forward this full picture for second Hammond enhancement in plasmon nanostructure is that you need fundamental excitation enhancement, and also you need second order emission amplification. But in addition to these two well-known mechanisms, you still need to pay attention to the symmetry breaking, because this symmetry breaking can switch on your second Hammond dipole coupling, or you switch off it to give you a very large second Hammond emission signal or cancel out the second Hammond emission. So in experiment, we prepare 2 classes of structures. That's the real nanoparticle dimer symmetrical structure and the particle on film system. This is what we call symmetry broken nanoparticle. So in the linear response, that's the dark field scatter response, you will find that the 2 structures show more or less the same response, the resonance. But you find that in the nonlinear response, if you excite these 2 structures with a highly focused laser femtosecond laser beam, you will find that only a few real nanoparticle dimers can be lighted up under the femtosecond laser illumination. But for the asymmetrical particle on film system, we can always observe very intense nonlinear emission signal. Very interesting thing, a very interesting phenomenon here is that for each nonlinear emission pattern, we observe a 2-lobe shaped emission pattern that's quite different from the real nanoparticle dimer system. And if you change the excitation wavelength to the resonant condition, you can even get a stronger nonlinear emission pattern. So what's the reason for that? And we found that from the spectral response, we have also observed that for the symmetry broken structure, we can have quite significant second Hammond emission signal, which is even comparable to the 2 photoluminescence. That's quite counterintuitive, is because the 2 photoluminescence is actually a bulk response for metals, but the second Hammond response is a surface response. But now with such symmetry breaking argument, we can even enhance that to be comparable to the Bonk response. On the other hand, if you look at the nonlinear emission from the real length pi dimer, the symmetrical case, now you will see a much smaller second harmonic emission, which is quite small, much smaller than the Bonk response. And this symmetry broken argument is also confirmed by measuring the second harmonic radiation pattern. So because in this particle film system, the second harmonic response comes from the virtual length particle dimer. So you will see that if you measure the second harmonic radiation pattern, you will see such donut shape. But for the real length particle dimer system, you will just see a solid spot. Okay, and this is also consistent with the second harmonic polarization pattern. And to further confirm that, you can rotate your excitation polarization. For example, you rotate that, you will see the long axis of the two lobes also rotate with that. So this is another evidence that we excite the vertical bonding dipolar mode in the particle on film system. And if you change your excitation polarization to the from the linear polarization, from the circle polarization, then the Z component in the focal plane actually becomes such donut shape. Then we also observe that the second harmonic radiation becomes, the emission pattern becomes a circular pattern. So this evidence suppose our previous argument that you need to break the symmetry and to get very enhanced second harmonic generation. And finally, if you do very careful calibration experiments, we found that we can increase the second harmonic conversion efficiency by 3 orders of magnitude, and we also increase the emission rate by 3 orders of magnitude increased to compared to the previous studies. Actually, this is not the end of story. You can replace this nanosphere by a nanorod to realize a one-dimensional nanocavity, or replace them by a nanocube to realize a two-dimensional cavity. Now, of course, you can place one nanosphere to close to another one to realize more rich plasma hybridization, and you can use these platforms to quantum plasmonics and cavity plasmonics. And so the second story I want to briefly introduce is actually we compare the optical response of a nanosphere dimer on silicon and a nanosphere dimer on gold. We found that due to the dimer, the coupling between the nanosphere dimer and the gold film, we can shrink the particles' localized surface plasma resonance by more or less three folds, and also gets a strongly enhanced scattering intensity. So this is the scattering intensity measured. So you see more or less threefold enhancement. So the reason for such shrinking or the enhanced quality factor of this couple system is because in this couple system, we actually can invoke the magnetic response or the electric quadrupole response. That's given by the blue line. And if you look at this, the nanosphere dimer on silicon dioxide, you see that the quadrupole response is very weak. So due to the presence of this electric dipole response and the quadrupole response, we get very efficient hybridization, and then we can store the energy into the system to get a much larger quality factor. So the good thing with this enhanced quality factor is that we can enhance the photoluminescence of the couple system by 200 times compared to the nanosphere dimer on silicon substrate. And also we get a very highly polarized photoluminescence response from the structure.
You have 1 minute.
Yeah, so this phenomenon can be easily explained because when you excite the plasmonic structures, you pump those p band electrons to the sp band, and then this sp band can couple with your localized surface plasma resonance. So because in our structures, the localized surface plasma resonance are highly polarized, so the radius decay of those localized surface plasma resonance, localized surface plasmas will also give you highly polarized photoluminescence signal. So the last thing I want to share with you is actually we found that the photoluminescence signal from such couple system actually comes from two very thin slabs of the metal film, and the very little signal comes from the gold nanospheres. Actually, in the nanosphere gap, we also have very large near-field enhancement. So this is actually a quite counterintuitive phenomenon. So we are still working on this, and hopefully we can extend this phenomenon to a nonlinear optics regime. And with this, I would like to thank you very much for your attention.
Thank you. Time's up. Questions?
Yeah,
okay. Yeah, Dr. Fang, you go ahead.
All right. So yeah, I think this is a very impressive result. I just wanted to ask you how to really take control of the interface. A lot of examples that you are providing assumes a perfect interface between code and the substrate. And a related question is how to harness the overall gain beyond one particles or one particular device.
Yeah, thank you, Nick, for these important questions. So actually, for the surfaces here, you notice that in our hybrid systems, we have nanospheres, we have metal films, right? For nanospheres, usually we use wet chemistry method to prepare those nanospheres. So they are single crystalline, they are single crystal structures. So their surface are supposed to be very smooth. And then the surface of the gold films we have to be very careful. Now in our study, we use a so-called template stripping method. Okay, so we deposit metal films on ultra smooth silica substrate, and then we use we use template stripping to pick off the metal film and use the other side as our metal film, and then push our particles on top. So with this method, we can significantly reduce the surface roughness from bigger than 1 nanometers to 0.4, 0.5 nanometers. So with this, we can have a better control on the particle film distance. Okay. Now to answer your second question, how we can take the overall gain when we put more particles together, right? So actually, this is give you a very good example. So when you have a single nanosphere on the metal film, due to the coupling, you can only have 2 resonance modes. One is supposed to be at a longer wavelength, somewhere above 800 nanometers, okay? And the other one is in the visible range. But now you notice that if I put, actually I should show you that slide so they help you better understand that. So you see that here, this is what I said, particle on film system. We can only observe 2 resonance. One is on in the long wavelength range, the other one in the visible range, okay? But you notice that this non-wavelength range resonance is quite broad. It's because this is a bonding dipolar mode. So its radiation is quite strong. So this is not good. Actually, the quality factor of this cavity is quite small. Now to overcome this problem, to solve this problem, when we put a larger particle here, you notice now that we have a new resonance that's in the middle wavelength range and with a quality factor more or less 3 or 4 times smaller than the long wavelength one. That's because of the efficient coupling between the bonding dipolar mode, this bonding dipolar mode, and this quadrupole mode, okay? And this quadrupole mode only appears when you have a conductive substrate, because this conductive substrate can significantly distort the dipole orientation. You see here, these 2 dipoles are more or less aligned in the horizontal direction, right? But with the presence of this conductive substrate, you see that you have this significant distortion. As such, distorted dipole moments can be decomposed into 2 horizontal dipoles and 2 antiparallel ones. So these 2 now can efficiently hybridize with each other to shrink or to increase the quality factor of the hybrid system. Yeah, thank you.
Right. Thank you very much. I think for the sake of time, I'm going to hand over to Mitchell.
Thank you.
Thank you.
Okay, so we will have our next speaker, Professor Howard Lee from University of California, Irvine, and he's gonna share his research with the title of Field Effect Tunable Meta Optics and Meta Optical Fibers. Okay, the stage is yours.
Hey, thank you for the introductions. I think you can see my slides. Okay, sounds great. So I'm Howard Lee. I'm an associate professor from University of California, Irvine, at the same time as the Optical Society ambassador as well. So first of all, I would like to thank you, the organizer, to invite me to be able to share the research with all of you today. At the same time as participate on this really great iCANX platform, at the same time this young scientist campaign here. So what I'm going to tell you today is a topic related to what we are doing in the research related to meta optics. At the same time, I will tell you how we make it tunable as well, and also how we can integrate this kind of meta optics into optical fiber platform. But before I go into details of my talk, let me just introduce a little bit more what exactly is this kind of meta optics is. So we sometimes call this a meta surface as well. You can think of this as like a ultra thin optics. Basically, we're making optics component in a really ultra thin dimension here. So if you take a look on this surface here, we're looking on the top view. Basically, this kind of metal surface, we have a scatter or nano-resonator on top. And using this kind of nano-resonator, you can actually shaping the light in different property you want. For example, like 10 years ago, the first report on this kind of metal surface in the Harvard group, what they're looking at, for example, normally your light will reflect in a normal direction, but using this kind of metal surface, they find some anomalous reflection or reflection here. So basically, using this kind of nano-resonator, nano-structure, you can basically shaping all the property of light, for example, the phase, amplitude, reflection, and scattering, and so on. So using this kind of a nano structure, nano engineering, you can shaping the light in a completely different way, in a nano engineering way here. But just to tell you how impressive on this kind of metal surface optics here, just to show you some of the structure here, this is a titanium oxide metal surface by the Harvard group, and we actually also fabricating similar structure as well. And what they can do actually making a lens when the light coming in, you can focus the light here. And if you take a look on the structure here, you can see that they're really ultra thin here. We're talking about maybe a few hundred nanometer in thickness here. And at the same time, compared with the bulky optics you have in your objective, in your microscope, you find they actually scale down significantly. At the same time, you can have similar functionality here. That's why this is really impressive. And not only for lenses, for example, mirror, beam splitter, polarizer, etc., you can kind of imagine you can have a metal surface, ultra thin version of this kind of optical component here. And that's actually why it's so exciting, is because you can basically scale down all the optical component in a really thin dimension, at the same time applying for making really ultra compact device and application here. And that's why in the last couple of years, there are a lot of really fascinating and really exciting application using this kind of metal surface. For example, people able to making really fun, really special beam, for example, voltage generations, ultra thin focusing lenses, controlling the polarizations, or even making a metal surface holographic structure. So this is a really exciting field. And in my opinion, this is one of the most hottest a topic in optics and photonics in the last couple of years. And not only because we can scale down the optical component, but at the same time, the physics is different. At the same time, you can also find some new functionality or device application from this kind of metal surface optics here. But still, if you try to take a look on most of the report on metal surface, they are mainly is a passive structure. What that means is that once you fabricate the structure, the optical property cannot be changed anymore. And this actually our motivation is want to make it tunable using some kind of conducting material here. And you can imagine, for example, making a lenses, conventional lenses, like my glasses, typically it's quite thick, couple of millimeter, but metal surface version could be really thin. At the same time, you can make it tunable. You can tuning the focus or even tuning different optical property actively here. So this is actually the motivation of our research. And I would actually tell you two topics here in this talk. I will tell you how we make this kind of tunable metal surface electrically. At the same time, I will tell you how we can actually integrate this kind of metal optics in a completely different platform, in an optical fiber platform here. And let me first tell you about making a tunable metal surface here. So the tunable material we're using is called a transparent conducting oxide, which is a heavily doped semiconductor. They have high transmittance and visible in near-infrared range. And they actually have been heavily used in touchscreen or solar cell application where you need a high transmittance at the same time the electrical conductivity. So the good thing for this conducting oxide material is actually you can actively control the optical property here. And the way we actively control it is using so-called field effect dynamic or gate dynamics. So basically it's like making a MOS transistor you learn in a solid state physics. You have a metal insulator and semiconductor here as an indium tin oxide. And now if you're applying the voltage, because you have an insulator here, your electron will build up at the interface, you accumulate the electron. As a result, you're increasing the electron density and you can actually changing the optical property at this interface here. And to show you this, you can see the simulation here by applying a couple of volts. You can actually changing the K density for maybe order of magnitude. At the same time, if you look at the permittivity of the material, that means a kind of a refractive index. You can see that you actually can change from positive to negative on this permittivity. What that means is that you can kind of changing like a dielectric property to metallic property just by applying voltage here. So you can see that really impressive. You can apply the voltage, the tuning optical property really efficiently And this is actually how we're using this mechanism to making a tunable metal surface here. So then we integrate this material into a land resonator metal surface and applying the voltage to actively control this optical property. And you can imagine like you have a resonator, then you're applying the voltage, you can change the mode, resonance in terms of the amplitude and phase of light can also actively change here. So then what you can also do is you can apply even different voltage to different antennas, for example, a few of them with one voltage, another few with another voltage. Then you can basically actively making a phase grating, let's say 0 pi phase change here. As a result, when your light coming in, because you have a phase grating here, you can deflect the light to a different angle here. So that means you can actively deflecting the direction of light using this kind of tunable metal surface. So to do this, basically you just need to gating the structure, maybe left and right and bottom with a different voltage here. And just to show you some of the structure we fabricated before, for example, you see there's some metal here, active material ITO, and then you see in the center we have antennas. And the antennas, you can see they all connect to outside, and also 3 of them is connected to each other. If you zoom in further, you see this kind of antenna is really also small. We're talking about a few hundred nanometer in size here. And at the same time, the great thing is like you can apply the voltage at the same time controlling the optical property at the same time here. So then just to show you the results, so you can see you have a reflectance resonance here by applying voltage. You can shift the resonance and you can change the reflectance for about 30% here by applying voltage. But more important is the controllable phase. We are able to demonstrate that we can have a phase shift of pi by applying a couple of volts here. So which is really important demonstration because this show that we can apply the voltage to control the phase and amplitude of this metal surface. And this actually the key things for tunable metal surface is to control the phase and amplitudes. And this actually is kind of the first successful electrical tunable metal surface we were able to report at that time. And at the same time, we're also able to demonstrate that we can spin the light. As I mentioned, we can gating the structure in a different way so that we can actively spin the light to different directions. We're able to demonstrate on 140 degrees of light spinning this structure here. And just to give you some performance, so this kind of gate tunability, you can potentially operate in gigahertz range. At the same time, could be quite low power consumption because we are applying only really tiny voltage here. So this is a kind of demonstration to control the phase and amplitudes, and we also demonstrate, for example, in different structure, we can make a tunable color filter using a similar mechanism by applying voltage. You can tuning the transmission band to different wavelength. At the same time, we're also able to demonstrate, for example, tunable absorber as well. We have a perfect absorber here. We can apply the voltage to tune the wavelength of operation of this perfect absorber here. So you can really see that this kind of mechanism, field effect mechanism, can really electrically actively control the phase, amplitude, or even transmission reflection of this kind of metal surface structure here. And just to remind you, this kind of tunable metal surface could be potentially using to tuning the focus, tuning different optical property when you have the transmission or reflections. There are actually a lot of different potential applications. For example, for your CMOS imaging system, you have a lot of different optical components. You can scale down all of this by using metal surface, at the same time having the active functionality, or using this for active spinning elements for light applications, or even using for virtual reality glasses, for example, because they have a lot of optical component holograph lenses inside. So you can using metal surface to scale down, at the same time using the functionality to add things some control there. So for this kind of AR, VR glasses. So actually we we report in a review paper recently. We try to figure out what kind of potential application we can use on this kind of tunable metal surface. We find there actually a lot of different potential impact on different kind of photonic application. For example, from optical communications to light application, light cells for the space, making laser device, or even image encodings, or even holograph, etc. So you can see there are a lot of potential really impact application using this kind of ultra thin active control of ultra thin metal surface component here. So this is the first part. In the next couple of minutes, I will tell you a little bit different platform. I will tell you how we can integrate this kind of metal optics into optical fiber platform here. So as you may know, the optical fiber is actually a really efficient guiding mechanisms. You can guiding light in the glasses using total internal reflections for really long distance because the losses of the glass is really low. And that's why you can use this for long distance communications. And that's why you have a really fast internet. And in my opinion, this is one of the most important innovation nowadays because without internet, you can't imagine how the life changed. For example, I cannot present with you live here. We cannot watch movie online. At the same time, we cannot go to this iCANX platform every Friday, etc. So the life will completely change without the internet. And that's exactly why the father of the fiber optic, Charlie Glau, got the Nobel Prize maybe more than 10 years ago on his contribution on using optical fiber for optical communication. And other than communications, there are other applications like optical imaging, sensing, and fiber laser. They actually have been really important technology for fiber optics. This have been really mature and have been really developed technology already. But still, as a physicist and scientist, we're kind of trying to see what kind of limitation we may have in this kind of well-developed waveguide. Basically, you still have a lot of limitation because you have limitation from the glass material you use itself. At the same time, the geometry you need to guiding the light is also limited. At the same time, once you fabricate the optical fiber joint, all the optical properties fixed, for example, the phase, amplitude, polarization, and mode profile. And this is exactly why in my lab we're particularly interested on, can we integrate some of the nanophotonic concept, for example, the ultra-thin metal surface, new material into optical fiber to develop a new kind of optical fiber so that we can have an advanced functionality, at the same time minimizing the fiber device components, at the same time using this as a new optical excitation platform here. For example, we can make a tiny component on the fiber end face here. So here, I will just show you one example, for example, to tell you how we can make a lenses, metal lenses, ultra thin lenses on the end face of the fiber so they can focus the light here on the fiber. So to making a lenses like my glasses, basically, typically you need a certain curvature of the lenses so that you can produce different optical phase path here so that you can focus in your light. So what that means is that you need a certain phase profile to focusing the light as a lenses. But in order to make an ultra thin lenses, basically what we do is using so-called geometric phase. Using these resonator elements, by rotating these resonator elements, you can basically changing the optical phase by changing the angle of this unit element while preserving this efficiency. So what's that mean? If you want to design these lenses with this optical phase, then what you need is just to rotate this unit element in a different rotational distribution here. So that is for one certain lenses. If you design another kind of focusing lenses, then you just need to decide with different distribution here. So this is how we design this kind of tunable lenses here, kind of ultra thin lenses on fiber. So then to fabricate, we're just coating. Okay,
sorry, one more minute.
So we're coating the gold on the surface, and then we're using a nanofabrication technique, focus ion beam technique, to milling the nanostructure on the fiber. And you can see this is some of the structures. You can see this in the core of the fiber. We basically gradually rotating this structure gradually from the center to the side, so that you can producing this kind of phase one to making lenses here. And this is one lenses. You can design different lenses by using different distribution here. But for those of you who are not familiar with optical fiber, so just to show you the dimension here, this is my hair, which is like 100 microns, and optical fiber is similar 100 micron, but we are actually fabricating at the center of the core, this kind of nanostructure, which is 1,000 times smaller than the hair. So we're really making really small nanostructure on the optical fiber, changing the optical property. So I will skip some of this demonstration here. We're able to making a focusing lens and show it actively. You can see the focusing effect, and at the same time we are kind of working on even making it tunable as well. We can actively control the focus in the optical fiber platform. And what we think is there are a lot of potential application in terms of imaging, medical application, for example, for fiber endoscope, you can actively control or even reducing the components for surgery, fiber imaging, or even trapping particle on fiber. For communication, you can use for more multiplexing conversion, or even are used for fiber device, for example, like pulse shipping, dispersion engineering, etc. So there are a lot of potential application and impact on this kind of metal optical fiber here. So I acknowledge my student at the same time, the funding agency to support the research as well. And that's the end of my presentation. And thank you very much for your attention.
Okay, thank you very much. And time for questions.
Okay, I must be the first one to ask the questions. Okay, yeah. However, very nice work. Actually, amazing. Yeah. My question is quite simple. I just want to know, you have so many potential applications. Did you think which one will be the killer application?
So yeah, there are many different, like for example, the tunable metal surface. I think this kind of LiDAR application is one of the quite important things. And at the same time, making ultra thin components, let's say even for example, in space applications, that's something quite exciting as well. But for the metal optical fibers, like I think the application definitely, for example, for fiber imaging inside the body, as I say, for example, endoscope, or even for imaging spectroscopy, or even laser surgery inside the body, which is something quite important because nowadays at the moment they are not even micron size as well. So most of them even millimeter size. So there are a lot of potential if we can adding the functionality at the same time, making really ultra compact design on this kind of metal fiber for medical applications and imaging as well.
Thank you.
All right, I'll follow up on that. Can I ask a question, Michelle?
Yeah, sure.
I just follow up on Professor Zhang's question. So, Howard, you just mentioned that for future applications, it might go for like a fiber imaging or spectroscopy. In both cases, we need to run through a range of wavelengths through the optical fibers. So in that case, how can we focus these light signals of different wavelengths? What are the potential ways towards that?
Yeah, so this is some active research at the moment, but people already, for example, recently demonstrate broadband focusing lenses. We can basically compensating the dispersion of the optical component using some nano engineering. For example, we can couple two resonators to compensate some of the dispersion. So people are already able to demonstrate, for example, broadband visible focusing with a chromatic dispersion focusing there. So which is really possible. So basically it's the same thing we apply in the optical fiber interface using this kind of technique to make a kind of a chromatic focusing effect here.
All right, thanks.
Okay, time's up. So let's move on. Thank you.
Thank you very much.
Okay, so our next speaker is going to be Professor Flavia Vitari from University of Pennsylvania here in the US. She's going to be telling us about high-resolution multi-scale bioelectronics enabled by titanium carbide MZINs. Flavia? Flavia, are you up?
I think you're mute.
I think you're muted.
My apologies. Thank you. Can you hear me now?
Yep.
Great. So it is truly an honor and a pleasure to have been selected as a finalist for the iCANX award and to have the opportunity to present my research here. Today, I will tell you about our work on high resolution multi-scale bioelectronics enabled by titanium carbide MXIN. So in the bioelectronic technologies like implantable brain stimulators, cochlear implants, and wearable sensors are powerful tools to address the societal and economic challenges posed by many disorders such as cardiac, heart, brain disease or Parkinson's disease, deafness, or chronic pain. Some of these technologies, like electrodes for brain and cardiac monitoring, have been a mainstay in the clinical practice now for decades. But some others, like brain-computer interfaces, hold the great promise of restoring lost function due, for example, to amputation or injury, but they're still in the research realm. Regardless of the specific application, all of these technologies rely on an interface between man-made electronics and biology. And despite years of research, there is still an unresolved issue that critically affects the performance of bioelectronic devices. And this issue is the fundamental mismatch between the electrical, physical, and chemical properties of these two domains. Biological tissues are soft and compliant. They are dynamic and moving. Think about your heart contracting at every pulses. Bioelectrical signals are carried through ionic currents in a fluid, and all materials are organic. Traditional bioelectronics, on the other hand, are rigid and static. These devices rely on inorganic materials such as metal and silicons. And in the solid conductors, currents are carried by flow of electrons or holes. And finally, manufacturing these devices is time-consuming and expensive, as it relies on processes optimized in a semiconductor industry. In my lab at Penn, we are developing novel bioelectronic technologies to study, diagnose, and treat neurological and neuromuscular disorders. Our ultimate goal is to translate these technologies to patient care and improve people's life. To accomplish this goal, we adopt a multidisciplinary approach that combines fundamental studies of nanomaterial properties with ad hoc manufacturing processes to integrate these materials into functional devices. And we then use our technologies to research neural function and disease in a number of models ranging from small animals all the way up to humans. Some examples of our technologies are wearable and implantable sensors for human clinical and monitoring and diagnostics, or transparent electrodes for basic science studies of brain function. So why are we interested in nanomaterials? Well, in recent years, nanostructured materials, especially carbon-based nanomaterials like carbon nanotubes, graphene, or MXenes, have emerged as promising alternatives to metals for safe and long-term stable bioelectronics. The main advantages of nanocarbons are in the broad range of properties, such as the high electrical conductivity, the high surface to volume ratio, the low density, and the low magnetic susceptibility mismatch with soft tissues. These materials can also be functionalized to enhance or add sensing modalities, and for example, have high photothermal conversion efficiency, which is advantageous in applications like theranostics or remote photothermal neuromodulation. In addition then to the peculiar material advantages, carbon-based nanomaterials can be easily processed with high throughput, low cost manufacturing, such as inkjet printing or direct laser writing. And in the last few years in my lab at Penn, we have extensively investigating the use of carbide MXenes for bioelectronics. As many of you are very familiar with, the term MXenes refers to few atom thick, two-dimensional nanomaterials consisting in a conductive carbide or nitride core, and a surface decorated with oxygen, hydroxide, or fluoride groups, depending on the synthesis process. Of the more than 20 forms of MXenes synthesized thus far, we have been focusing on titanium carbide MXene, or TF3C2, since it was the first to be synthesized, the most extensively characterized, and the best performing at the moment in terms of conductivity and capacitance. Now, what makes MXene unique among other carbon-based nanomaterials is that in addition to all the other properties I just mentioned, it is hydrophilic and stable in water without any surface functionalization. This means that we can make MXene-based inks that are safe and processable at room temperature, and that are common with polymers used for packaging implantable devices such as silicon, peridine, or epoxies. Since TF3C2 is relatively a new material in the field of bioelectronics, in the early stages of this work, we had to put significant effort into developing a process to reliably produce implantable bioelectronic devices with MXene. The resulting process flow is a sequence of conventional photolithography and metal lift-off steps integrated with liquid phase processing of the MXene ink to micropattern the electrode sites, in this case, onto a peridine substrate. With this process, we successfully fabricated microelectrode arrays with different geometry. The first one is a planar device with all MXene contacts to record brain signals directly on the surface of the brain. And the second configuration is an invasive electrode that penetrates the brain tissue where and the MXene contact lies next to gold contacts of the same size for side-by-side comparison of the recording performance of the two materials. When we measure the interfacial electrochemical impedance of the MXene and gold contacts, and this is an important property for noise-free recordings, we found that it was not only in the range required for neural recordings, but actually was significantly lower than gold. And when we use then these electrodes to record signals in vivo inside the brain, we found that the improved impedance of MXene resulted in a much higher sensitivity and lower signal-to-noise ratio, and an overall broadband improvement in the quality of the recordings with MXene. And with additional characterization, we attributed the superiority of MXene to both its higher capacitance and higher electrochemically active surface area compared to gold. Importantly, in the same study, we demonstrated for the first time that TI3C2 MXene is safe to neurons and actually can support healthy neuronal function and growth. Now, clean room fabrication is ideal for making small devices for basic neuroscience studies, but really does not scale well for devices that have to cover large portions of the brain like it happens in humans. So for these applications, microfabrication is time-consuming and expensive and optimized for patterning microscale features, but really does not scale well on the millimeter to centimeter scale. So to evaluate whether MXene could also address some of the resolution and comfort issues of the human scale bioelectronics, we devised a rapid, high throughput, and high yield fabrication process for making large scale devices still based on MXene aqueous inks. The process briefly involves laser machining and absorbent substrate to create the electrode contacts, followed by inking with MXene. The device is then encapsulated with an elastomer, typically PDMS, followed by selective etching to open up the electrode contacts. And this process produces planar structures that can be used, for example, for wearable sensors that can go directly on the skin. For applications like electroencephalography or EEG, where the brain signals are recorded directly on the scalp, so there's a hair in between the electrode and the scalp, we slightly modified the process to add three-dimensional mini pillars and overcome the hair barrier. These mini pillars are made with cellulose foam infiltrated with MXene, and then the rest of the fabrication scheme is the same as that of the planar electrodes. In addition to being significantly faster than microfabrication, this process is high throughput, low cost, and scalable, and can be conducted at benchtop in any laboratory settings and without specialized equipment. And also, we can really fully customize the shape, size, and geometry of our devices. The resulting electrodes, which we also call MAXtrodes, are composed by conductive MXene cellulose traces and soft porous MXene cellulose aerogels at the scalp contact sites for improved contact and comfort and signal quality. The close-up images of the array surface show MXene flakes well interpenetrated into the entangled structure of the substrate. And this is also shown by the prominent MXene peaks in the XRD and Raman spectra. And the presence of these peaks also show that the process is actually preserving of the MXene structure and non-damaging. We then benchmarked MXene electrodes against commercial clinical electrodes made with platinum and measured again the electrochemical properties that are relevant for recording and stimulation of bioelectric signals. We found over 20 times improvement in the electrochemical interface impedance and more than 30 times higher charge storage capacity for MAXtrodes compared to platinum, which implies an improved ability of these devices to store charge and then release it for safe and effective electrical stimulation. Again, we attributed this enhanced electrochemical performance of MXenes to the higher surface area and the capacitive nature of the MXene interface compared to the smooth surface of platinum. For stimulating electrodes, the electrochemical stability under repeated pulsing is of a paramount importance. So we subjected the electrodes to accelerated electrical aging tests with 1,000 cycles of controlled current stimulation at 1.2 milliamps. And we did not observe any change in impedance response before and after stimulation. We also confirm the excellent mechanical stability of MAXtrodes under repeated bending. In addition to the favorable electrochemical behavior, the physical properties of MXene make it ideally compatible for application in conjunction with clinical neuroimaging, such as computerized tomography or CT and magnetic resonance imaging or MRI. MXene density is more than 5 times lower than that of metals like platinum, which results in almost no artifact from X-ray scattering when these devices are imaged in the CT scan. And what we didn't know, and we demonstrated for the first time in this study, is that T3C2 MXene is weakly paramagnetic with a magnetic susceptibility that is much closer to human tissues than that of platinum. And as a result, we found that MXene does not give rise to imaging artifacts even under high magnetic fields. We also confirmed the magnetic compatibility of MXene in humans by imaging our MaxStro devices during functional MRI sequences, which have particularly stringent artifact requirements. And as you can see here, because I had to draw the outline of the electrodes, the devices are basically invisible and do not cause any artifact or distortion to the brain structure, which really opens up new and exciting opportunities for applications of EEG in combination with imaging that can significantly impact neurological care. To demonstrate the clinical utility of MaxStrodes, we benchmarked them against clinical EEG electrodes. These electrodes are typically made out of metals and require a gel to overcome the hair barrier. The main drawback of these gels is that they are irritating and uncomfortable for patients. In this test, we placed the MXene array on the scalp without gel, and then at the center, a clinical electrode with a gel underneath. The impedance of the MXene electrodes and gel electrodes is comparable, which indicates a good contact of the dry MXene electrodes with the scalp. And the brain signal recorded with the two types of electrodes is virtually indistinguishable, not only at the representative location, but actually across the entire array. Given the high sensitivity and resolution of the MaxStrodes, we can now start pushing the boundaries of brain recordings. For example, we made grids of very high density electrodes covering a small, like 2 by 2 centimeter area of the forehead. And we recorded the brain activity. So in this video, you're going to see the power of the EEG signal on the electrodes over time. The EEG trace on the top corresponds to the electrode outlined in the bottom panel on the left. As you can see that there are distinct patterns of brain activity that emerge at the centimeter scale, which is much lower than previously believed. And so now with the ultra high density EEG grids, we can start unveiling brain dynamics that were previously hidden with other non-invasive EEG devices. In conclusion of this talk, I would like to just mention that we are leveraging the enhanced material properties of MXene and the versatility of the fabrication process to explore a wide range of applications of these electrode interfaces beyond scalp EEG.
1 minute.
As you can see from the cover of Science Translational Medicine that featured our work earlier this year, some of these applications include high density wearable muscle sensors, eye sensor for detecting retinal pathologies, as well as invasive electrodes for recording and stimulation during neurosurgery. And then in conclusion of this talk, I would like to acknowledge my talented students and postdocs, my collaborators, and I want to thank you again for the opportunity to present here and for your attention. Thank you.
Thank you very much. Very good presentation. Questions? Maybe I can get started. With the materials that you're making for soft tissue, how do you interface them with the regular electronics? Because they're soft, they're delicate, but transistors and semiconductors are hard.
Yes, this is a really good question. And one thing that I didn't mention is that actually we had to put a lot of effort into figuring out also the interface between our devices and the regular electronics. So we have figured out a welding method that works pretty well between the MXene traces and the PCBs that we use, and that method is based on conductive silver or carbon-based epoxies. And in this way, we can achieve a good conductivity and record signals with good qualities. For the thin film Perlin-based electrodes, we actually use regular connectors, and we are able to interface these devices with regular connectors with no issue in conductivity and arising noises.
Any other question? Yes, space for one question.
So I have a quick question. What's the advantage of using mixing over other 2D materials such as graphene, for example, 2D for TMDC or even nanotube nano network? Yeah.
Yeah, so there's one really, the main advantage is the conductivity and high capacitance of mixing. But there's another great advantage, which is the processability in aqueous solutions. So with graphene and other carbon-based nanomaterials and nanotubes, you really need to do surface functionalization, use surfactants or superacids, right, to keep this material stable in some liquid phase dispersions. With mixing, they are stable in aqueous suspensions, which means that we can easily then apply or use any liquid phase processing method at room temperature to make devices out of mixing. And really this lowers down significantly the cost and the time of our fabrication process.
Okay, thanks.
Thank you very much.
Thank you.
I hand over to Miso.
Okay, I'm very excited to present our next presenter, Professor Discharge from University of Pennsylvania. And he'll be sharing his research with the title of Strong Light Matter Interactions in Atomically Thin Semiconductors. Okay, so it's the stage is yours. Also, I think you're muted yet.
Are you able to see my shared screen?
Yes.
All right. Well,
Okay.
Thank you, Miso, for that kind introduction. So as was presented, I will be talking about strong light matter interactions in a very, very thin semiconductors. So let me give a very brief overview of my research group at Penn. We are a relatively young research group, and we work on several different areas of electronic and optical materials and devices. But today, in particular, I will be focusing on this particular area, which is nanophotonics and optoelectronic devices. And here I will be particularly focusing on two-dimensional or atomically thin excitonic semiconductors. So to get started, let me give a very a broad and brief overview of low-dimensional excitonic materials. They have been known for a long time, and they have been investigated for a long time, and they form the basis of a lot of modern optoelectronics technology. For example, the field really started with epitaxially grown 3-5 epitaxial growth 3-5 quantum well materials, which have been used for optical modulators and lasers for a long time. But more recently, the naturally occurring low dimensional one or bottom up grown low dimensional excitonic materials have sort of kicked the research into new directions and has led to a very enhanced activity in research. Organic small molecules and polymers are very well known. They have now been investigated for over 2.5-3 decades. Like wide colloidal crystals and carbon nanotubes have also been heavily investigated. Our group works on all of these materials with the exception of epitaxial 3-5 quantum wells. But the most recent ones have been two-dimensional transition metal dichalcogenides and two-dimensional perovskites. And these are the ones that I will be focusing on the most as part of this talk. And one of the things that makes these excitonic materials in low dimensional particularly exciting is that because of the low dimensionality, when you excite an exciton in these materials, the electric field lines can actually penetrate out of the material owing to the low dimensionality, and this leads to strong binding forces between the electrons and hole, as a result leading to higher exciton binding energy. And this higher exciton binding energy enables strong excitonic properties even at room temperatures. And this is something that has always been lacking in bulk or three-dimensional excitonic materials, and therefore this opens up a whole new gamut of applications as well as fundamental science investigations. So the idea of coupling or understanding a coupling between excitons and photons is not new. It's a fairly old idea, and people have looked at it in 3-5 quantum wells at cryogenic temperatures for a long time. In fact, there have been very exciting proposals in optoelectronic devices to look at condensates of excitons and photons, since both of them are bosons in nature. The idea of Bose-Einstein condensate of exciton polaritons and that leading to lasing applications has been explored for a while. However, the problem with the conventional excitonic quantum well-like materials is the epitaxial growth and the 3D character or 3D bonding character. With the advent of two-dimensional van der Waals or atomically thin excitonic materials, you now have the ability to not only separate them and place them onto arbitrary substrate, but you can also change the cavity medium to any arbitrary optical cavities. So things like plasmonic resonators or dielectric resonators or photonic crystals all become fair game in terms of integrating them with these novel class of two-dimensional excitonic materials, an exploration of a lot of interesting fundamental light-matter coupling phenomena. So this has been explored by a few groups over the past few years. We have recently summarized this in a very nice review paper that came out 3 or 4 months ago in ACS Nano. Please take a look at it if you get a chance. And so one of the main reasons we have been interested in the first class of excitonic materials that I'll be talking about, actually I will be talking about them for most of this talk, are these TMDCs, the transition metal dichalcogenides, semiconducting two-dimensional materials of molybdenum and tungsten primarily. And they have this layered structure, as many of you may know. And one of the most interesting things in my view about these materials is that even though you make many layers of them or make them very thick or bulk in nature or electronic bulk in nature, their optical constants are still highly dominated by excitons. And you can see that in their optical dielectric function. This is of bulk WS2, for example. The other interesting thing, which often gets overlooked in these materials, is that the extremely high refractive indices. Refractive index more than 4, even below the absorption edge, is something unheard of or not seen very commonly in most materials. So they are really materials with very high, both real and imaginary part of refractive index or optical constants. Right. So originally we were interested in looking at these materials for photovoltaic applications. And one of the reasons we were interested in that is because they have very favorable band gaps, right around or close to 1.3 electron volts, which is favorable for solar energy harvesting. But more importantly, they are some of the strongest absorbing semiconductors that we know of. They have absorption coefficients higher than most known photovoltaic semiconductors or most known semiconductors, period. Right. So this was our motivation. And the idea was, how do you exploit these large absorption coefficient yet use their small thicknesses to sort of trap maximum amount of light? So we did a lot of work in this area in photovoltaics. This is older work, so I don't want to emphasize it too much. But the problem that comes together with high index and high extinction coefficient is that when you make things a little bit thicker, it starts getting reflecting. So if you see like bulk WS2 crystal, the mismatch in refractive index with light coming from air into this high index medium is so large that most of the light starts getting reflected. But if you make it too thin, then most of the light starts getting transmitted. So where is this balance where you can actually have most of the light be trapped or absorbed into the medium, right? And so you want to do this, but you want to do this in a scalable as well as an efficient way, or even cost-effective way. And so to do that, we took this approach of putting these thin materials, 10 to 15 nanometer thick crystals, onto reflective gold or silver substrates. And so because of this large mismatch in refractive indices combined with the reflection from the backside and phase propagation of the light that happens while the wave travels in the medium, because of the high extinction coefficient, you can have destructive interference occurring at the top surfaces in such a geometry, and even for deep sub-wavelength thicknesses. Okay, so now the wavelengths we're talking about are visible frequencies, but the thicknesses we are talking about are just couple tens of nanometers. So even in deep sub-wavelength thicknesses, you can get nearly perfect absorption. Okay, so this was quite an amazing thing to sort of first come up with, and then even demonstrate it experimentally, and this is all highlighted in these papers. But then we wanted to actually look at more interesting phenomena over here, that if you are resonantly trapping light in a material without any other optical cavity that you are other optical cavity that you might otherwise need, what happens to the excitons? And so to look at that, we started doing these calculations first, where we started looking at how does the reflectance spectra of WS2 vary as a function of thickness. And what we found is that at large thicknesses, you have this single mode that you see, which is the typical exciton resonance at about 2 electron volts. But as you go to smaller thicknesses, at about 15 nanometers or so, this mode splits into two modes, namely upper exciton polariton and lower exciton polariton. It actually interacts with this Fabry-Perot-like cavity mode, which has this linear dispersion, as you can see, as a function of thickness. And most importantly, this simple transfer matrix calculation actually done by a second-year undergraduate student matches very well with experiments. And the points taken from experiments when put on this graph, you can see that these are the circles over here. They actually match very, very well with theory and even to a simple two-coupled oscillator model, which are these dashed lines. All right, so this was very exciting to see. And we saw that this can be seen in all other excitonic TMDCs on other reflective metal substrates, such as even silver and aluminum. Right, on aluminum, it is particularly strong, as you can see. But you cannot see the same thing on three-dimensional materials, which have similar band gaps and similar refractive indices, such as gallium phosphide and gallium arsenide. And so it is important for the optical dielectric function of the semiconductor to have it localized, or the local density of states localized in excitons in the form of these sharp peaks for such kind of coupling to observe. If you don't have that, such as flat band edges that you see in three-dimensional semiconductors, you are not going to see this strong coupling-like behavior. Okay, so to sort of take this further, we took it a step further and actually now broke symmetry in plane by actually nano patterning resonators over here. And if you do that, you are able to break the symmetry along one direction and preserve it along the other direction of polarization of light. And you start getting these other interesting modes which are plasmon-like in nature. We were able to verify these modes are plasmon-like in nature by doing FDTD simulations. As you can see, these modes are localized at the interface of gold and WS2, and you can also verify them very well in experimental spectra, these points from experiments taken and then superimposed onto calculations. So here is one example showing you how, as you vary the width of these resonators, you can see first, second, third, and fourth order plasmon modes emerging as you sort of pattern these WS2 in resonator widths. So all this was summarized in this nice paper that was published last year. But the key question that remained burning in our minds is what happens to monolayers, right? We have already demonstrated or shown that in few layer thick TMDCs, you can trap light really well. You can trap nearly 100% of the light over a fairly broad part of the spectrum, especially when there is a strong coupling going between excitons and photons. But it is also well known that a few layer TMDCs are indirect band gap in nature, right? As opposed to that direct monolayer TMDCs are direct band gap in nature, and they can also emit more light. And so these are potentially more interesting, but the problem is how do you trap light in sub-nanometer thickness, right? Now, each monolayer is sub-nanometer in thickness, and it's difficult because trapping of light at a very, very deep sub-wavelength becomes much harder. So we postulated some ideas about this back in 2017. One of those ideas was used as for use of a spacer with a reflector, but this can only again give about 40% of the light. And it was actually demonstrated by Young-hee Lee's group in Korea back in 2017 itself, right after we postulated it. But we were not satisfied with it. We wanted to do more. So we started looking at multi-layer stacks with varying refractive indices. So if you have such a multi-layer or artificially made quantum well stack, you can have light bounce around in this and actually get trapped for just 5 or 6 unit cells at about 90 or 100%, at least at the exciton wavelength, by just stacking them again without the need of any external optical cavity. So we were able to demonstrate this using wafer scale two-dimensional materials grown via MOCVD. This was again a very nice collaboration with a couple of other groups and companies. And here we show that you can actually artificially layer and stack these van der Waals quantum wells or optical superlattices or excitonic superlattices with TMDC spaced by dielectrics such as alumina or hexagonal boron nitride. What you can also observe in these cases, if you couple light at an angle, you can once again trap the light into resonant modes that can strongly couple with the excitons in the system, leading to splitting of exciton polaritons, especially at high angles or high wave vectors of the light coupling inside. And once again, the theory matches very well with the experiments. This work just came out 2 weeks ago in Nature Nanotechnology, and we have extended this work further to perovskite crystals. Perovskites are naturally occurring optical or van der Waals superlattices. These are alternating organic and inorganic materials. You can get large crystals made out of them, which are phase pure now. This is in collaboration with our collaborators at Rice University. And you can once again see very sharp optical resonances in these materials if you take spectroscopic ellipsometry. The interesting part is, once again, these crystals, they are direct band gap in nature, even in the bulk state, because of the organic spacers. The organic makeshift spacers prevents enough separation of the wave function in individual layers that they retain direct band gap. And you can also trap light very easily in them for very small thicknesses. But most importantly, you can once again see polaritons or exciton polaritons in these crystals without the need of external optical cavities. And now, because these are direct band gap emitting materials, you can actually see polaritons in the emission spectroscopy at room temperature. So now we can see exciton polaritons under emission at room temperatures, and they're very excited about this because this paves the way towards sort of looking at polariton photovoltaics or polariton photocatalysis, as well as the lasing and so on and so forth. So that is some of the areas we are looking at. This again was published 3 or 4 months ago in Nano Letters. So with that, let me summarize and give a broad outlook that actually few layer or bulk TMDCs are also very interesting optical materials, and they have very large optical constants with strong excitonic character. And all these monolayer to bulk 2D semiconductors are very interesting for novel integrated photonic applications because they have high index, they are easy to integrate and fabricate, and they support excitons which are highly tunable and highly nonlinear, which I did not talk about. And the path forward to application is really scaling them up to wafer scales, both monolayer and bulk, and integrating them into complex repeating units such as these quantum well or super lattice structures. So with that, I would like to thank a very hardworking group of students and postdocs and large number of collaborators and funding agencies that support our efforts across all domains. And thank you all once again for giving me this wonderful opportunity, and I'm happy to take any questions.
Okay, thank you very much. So time for questions.
Yeah, thanks for a very good talk. Impressive results you show. I think for many of the effects you show, substantial light input powers are needed and so on. So I was wondering, how stable are these materials, especially under practical conditions where there is plenty of oxygen, water, etc.?
Right. So this is an excellent question. What I would say is that we have been shooting powers of the order of 10 suns, so 10 times the solar radiance on two-dimensional chalcogenides, and they have remained perfectly stable for several minutes of measurement at least. Okay, and these are laser powers, of course. We haven't shot broadband powers yet, and so in that sense, the two-dimensional chalcogenides are quite stable. But you are absolutely correct that these perovskites are not very stable. And so what we have been doing with perovskites, especially if you want to go to room temperature powers, is encapsulating them with boron nitride. And with boron nitride, we have seen that you can survive up to 5 suns, 5 times the solar intensity, and you can keep doing it for many days, in fact, or many times the region, and they survive fine. But yeah, if you go to 100 suns, you'll still burn them.
So there is still a lot of research required there.
Yeah, I think at the chemistry level and also encapsulate.
Yeah, but do you have maybe ideas what fundamentally need to be changed at these materials to improve their stabilities?
Right. So I think this is a great question. And one of the things why I think perovskites are unstable under large illumination is the ionic nature of the bond. And so the bond is much more ionic for metal halides. And so I think this goes down to basic material science and chemistry. Can we find combination of metal plus a non-metal which can form less ionic bond, and also find combinations where you don't have the cation sitting in middle of this perovskite layer that is organic in nature? So like, for example, cesium lead bromide, right? That at least gets rid of one of the problems of removing the this organic cation that sits in the middle of the perovskite box. But in terms of fundamentally changing lead versus halide structure, I think there much more work is needed. Maybe tin is an answer, but I think there is a lot more opportunity to explore there.
Yeah, I completely agree with you. Yeah, but I also had a question about large-scale production of these materials. You showed some slides where you where you claimed you had wafer scale production, but this slide, for instance, yeah, the flakes are quite small. So how are you going to solve that issue?
Right. So again, good questions. I think for TMDCs at this point, we have 8-inch wafers, right? So, and the TMDCs are entering at least pilot scale demo production in certain foundries. So as far as 2D materials are concerned, namely 3 2D materials, graphene, boron nitride, and TMDCs, you can admit that they have been scaled up with fair amount of quality. In terms of perovskites, you're right. You cannot make single crystals more than a couple of centimeters, right? So these are highly phase pure single crystals. And if you look at the solar cell world of perovskites, people have been mainly spin coating them. So I think with spin coating is probably the only way to scale up, perovskite materials, because we wanted to make or measure phase pure optical properties, and because they're highly anisotropic, we had to use single crystals.
Yeah. Okay. Thank you.
Okay. Unfortunately, time's up, so we have to leave Professor Discharge at this time. So, okay,
thank you
let's
again.
move on. Okay, thank you.
Thank you. Our next speaker is going to be Haiding Sun, University of Science and Technology of China. He's going to be telling us about wide bandgap semiconductors for UV light emitting and detecting devices. Professor Sun.
Hello, good morning, good evening. Hello, can you see and hear me?
Yep. Mm-hmm.
How the slides is okay?
Yeah, you're good. Go.
Okay, great. All right. Hello, everyone. And my name is Haiding Sun. I'm from University of Science and Technology of China. I'm really honored to participate in this event, and I'm really thankful to iCANX platform, which providing us a wonderful platform to share our exciting research in the community. And today, I'm going to share our research on the wide bandgap semiconductor for ultraviolet light emitting and detecting devices. So in my presentation, I will have four sections. First, I will introduce what is gallium nitride semiconductors, and then I will move on 2 types of devices: the deep ultraviolet light LEDs and ultraviolet photo electrochemical type of photo detectors. Then I will conclude my talk. So first of all, let me introduce what is gallium nitride. And people already see from the left, like you guys probably already found that those kind of light bulbs is almost unavailable in the supermarket anymore, because due to the invention of the blue LED chip combining with phosphorus, we are also able to generate white light. And it is due to the invention of the blue LED chips and the lasers, and the 2014 Nobel Prize in Physics was awarded to the 3 Japanese professors. But the gallium nitride is not only for LEDs, right? It's also for lasers, for power electronics, for 5G, RF, for radio frequency transistors, X-band radar arrays, as well as for a lot of microsystem memory systems as well. So what is unique, and there's a lot of important material properties for those gallium nitride. They are direct bandgap material covering from the infrared to deep ultraviolet, and this can be doped in N-type and P-type. So the material can also be grow heteroarchitecturally on silicon carbide, and sapphire. And importantly, they have high thermal conductivity, and most importantly, they have very high, strong chemical resilience. Basically, they can apply, those devices can be implemented in the extreme condition, for example, in the space, in the seawater, or in the alcohol, or in the liquid acid, all kinds of environment can sustain a long time. So, and those materials are all semiconductors, which are environmental friendly. So our groups have been working on the ultraviolet since my PhD study. We have been working on the ultraviolet devices, and we are working on UV LEDs, UV laser diode, and the UV photo detectors as well. So, and for the UV optoelectronics, due to the high photon energies can be generated from the UV, and this can break the DNA structure easily. So those UV light can be used for water, air purifications, disinfections, optical therapies, as well as UV curing as well. And for system level, people can use those UV optoelectronics for photolithography, space exploration, and industrial use. And to give you an example, due to the breakout of the COVID-19, we are suffered a lot globally due to this disease, and we wanted to find an effective way to kill those viruses. So one of the effective way is we can use the UVC light or deep UV light to kill the more than 99.9% just in a few seconds illumination. So this technology is booming and it's becoming a very hot mainstream technologies used and a light source for killing those viruses, not only for COVID-19, but also for a lot of diseases as well. And this technology, and we have been working on this for a while, and almost since my PhD for about 10 years now. I would like to introduce what we have done so far. And as I mentioned, the UV LED market right now is booming, and due to the breakout of the COVID-19, and we are looking for efficient UV LED technologies. So, and compared with conventional way to kill those viruses or eliminate those viruses by the alcohol, chemical, heat, and people use the mercury lamp. And the mercury lamp technology is being mature, right? And it's people used for a while. But the mercury is toxic, fragile, and it's a short lifetime. Compared with, as the right show here, this tiny LED chip can exactly perform as a mercury lamp and can be compact structures and low energy consumption and a long lifetime and environmental friendly, unlike the mercury. So unfortunately, those LED, and especially when you move the wavelength, go to the shorter wavelengths, the efficiency drops significantly. And right now in the 250 to 280 wavelength range, and the efficiency less than 5%. This is too low compared with blue LED chips. Right now, the blue LED chips, the efficiency is about more than 50%, but 5% is too low here. So we wanted to improve it. There's many ways and there's many factors to be considered. First of all, how to improve internal quantum efficiency, how to improve the electrical injection efficiency, and how to improve the light extraction efficiency. All those factors take a role here for the high efficient LED. So from our group, we work on the architecture growth, how to obtain high quality material, how to design and restructure the conventional LED structures. And for example, use micro LED or nanowire LED. And lastly, we integrate the LED with special design device and to boost the efficiency. So I will go through one by one here. First of all, we go through the architecture growth process to overcome the material quality and also efficiency problems. For the blue LEDs, we have strong phase separation inside the indium gallium nitride quantum wells because the indium atom and the gallium atom, they have very large atom size difference. As a result, when we create such quantum wells, as you see here, we are able to naturally create compositional inhomogeneity. And as a result, the carrier can be highly localized inside the quantum well. It cannot move around. Thus, the only way is to recombine to generate blue light. But for those algan thin films, aluminum and gallium atom has similar size. The only way we can create is a very flat quantum world, as you see here. But we introduce a miscut sapphire substrate, as we show here. The miscut sapphire substrate will lead to a fluctuation, generate a wavy quantum world, as you see here. This naturally create a compositional inhomogeneity and lead to a highly localized carrier centers. And what we lead to is a significant boost of the luminescence, and we create one of the highest internal quantum efficiencies in the world. And this work has been highlighted in the Compound Semiconductor magazine. And this is me, I'm holding a wafer. And this work also has been commented and as a breakthrough in the deep UV by the editor of the magazine. And besides, we also created a way to extract more light, right? Not only to generate more light, but also the way to extract more light is also very important. Is here we introduce a hybrid pattern sapphire substrate. Basically, we combine the silicon oxide with gallium nitride and aluminum oxide with gallium nitride. Basically, we introduce a large reflective index contrast between this, and more light can be escaped from the sapphire side. What leads to is we boost more than 30%, 40% light output power compared with blue curve shows that this is a conventional one. All right, previously we discussed about the architectural growth innovation and try to overcome some issues. And then we go to the chip geometry design. We introduce micro scale LEDs as well as nanowire LEDs. Here we show you the conventional, we have large chip LED like on the left. Now we move to the 20 micro size. What do we learn from this experiment? And the demonstration, we show that a very high current density as shown here in the smaller device. And surprisingly, we have higher external quantum efficiency in the large current injection regime for those micro LEDs. But when we shrink the device down to a few micro size, for example, here, the sidewall or the edge play a significant role affecting the light propagation path. So what angle should be appropriate, right? So we experimentally demonstrated that 35 degrees is the highest. Meanwhile, this is verified by a theoretical FDTD verification that 35 degrees seem to be the one of the ideal angle for those sidewall. All right, so we already make a good single micro LED chips. To have high power output, right? We need to integrate them in, manufacture them into array. So here is we demonstrate the micro LED arrays in the emitting in the DPUV. And what we learned from the conventional LED big chip, the black curve, and the red curve is the micro LED array. They have exactly the same illuminating area. And what we found that the luminescence, the light output power can be improved by 52%, and external quantum efficiency can also be improved. So the micro LED shows a promising for the future. And lastly, we also use nanowires LED on metal. People will think why we wanted to use metal substrate, right? We usually use silicon or other regular substrate, but we propose to grow nanowires on metal. Metal has very good heat dissipation channel, and metal can be used directly as a contact. You don't need to make more contact, right? You just use metal substrate as a contact. So what we found that is that at high current injection, more light can be generated. And surprisingly, we found that more at high current injection, we found the efficiency doesn't drop. Basically, we demonstrate a droop-free behavior of the nanowire glowing on the metal. And because metal has very unique feature, as I said, high heat dissipation channel and directly making the contact. All right, now we move to the last part for the LED part is we monolithic integrate the LED with different structures. As you can see, this is a typical LED structure. Half of the light generated inside the quantum wells go to the above, but half of the light going to the bottom, and those light will be wasted, right? What if we integrated a detector here? And we combine a detector with an LED. Here is the structure we propose. Basically, here is the LED. This is the detector. Now, what the detector play a role here is the photon generated here. Half of them go to the air, right? Will be extracted. Half of the light go to here and being wasted. Now we have a photodetector. This photodetector will absorb the light, generate electron hole pairs, and this electron hole pairs will be re-injected into the active region to participate into the radiative recombination. As a result, this is the entire process. I will not go into the details, but the result is very exciting that we achieved one of the highest wall plug efficiency in the world to make the highest efficient LED here is by using this unique structure. All right, I finished the UV LED part and now go to the UV photodetectors. Photodetector has been commonly used in our daily life, and I believe most of people know how to make photodetector, and it can be used for X-ray detector, UV detector, and visible detector as well, and covering the entire solar spectrum band, right? And it can be used in many industry and daily life. I will not go to the details. This is a packaged photodetector, and people know as well. And for making UV photodetector, we use ultraviolet wide bandgap photo semiconductor. Gallium is one of them. In our group, we still use nanowires for the photodetector development. Why? Nanowire has dislocation-free property and it does not require strict architectural growth, right? For the thin film, you need to match the lattice match, but for nanowire, no. We can grow them on metal, on silicon, on sapphire, or any substrate. And due to the large surface to volume ratio, a lot of light can be absorbed by this nanowire due to the scattering and so on and so forth. And uniquely, if we put nanowire into an environment, because due to the large surface to volume ratio, we are able to interact this semiconductor with liquid or electrolyte. So this is, people demonstrated gallium nitride nanowire for water splitting, to capture the carbon dioxide, to generate organic chemicals, and so on and so forth. And thus, we leverage the gallium nitride nanowires to be used for the photoelectrical photodetectors, because of gallium nitride is chemical stability is high and can tunable band gaps for a lot of light absorption. So here is the example of our recent work. And what we propose to use aluminum gallium nitride nanowires, and this nanowire under the light illumination, and due to illumination generate electron hole pair. Electrons will go into the hydrogen evolution reaction as shown on the left, and the holes will be going through the photoelectron working station, going to the counter electrode. This is step B, and eventually the photocurrent will be acquired in the photoelectrical working station. This is photocurrent acquisition. Due to this principle, we are able to manufacture solid brand of PEC-PD, and we are able to make a p-n junction-based photo PEC-PD, and we are able to use 2 electrodes here to make double band photodetectors as well. And lastly, due to the photo plasma effect, we decorate those nanowires with plasmonic effect metals. We are able to generate broadband photodetectors as well, based on the PEC process. So I want to highlight one recent work, and which we create a bidirectional photocurrent in a single p-n junction nanowire.
You have 1 minute.
Okay, so this is a p-n junction, and this p-n junction have a unidirectional current. So what we learned that we have under 245 nanometer illumination, we are able to generate a negative photocurrent, and under 365 nanometer illumination, we are going to positive photocurrent. This has been published in the Nature Electronics recently, and I will not go into the details, but the principle is different reaction going to happen under the N-type and the P-type nanowires, and generate different type of photocurrent. In the end, I would like to show that we are able to get positive and negative photocurrent in the different wavelength band. Here we show is the negative, and here we show is the positive. And this can be used for a lot of applications: bio, optical communication, imaging, and color discrimination, optical logic. And I would like to conclude my talk. And our group work on the high efficient light emitting diode, and we have a lot of patents. We are going to commercialize this technology. Meanwhile, we are working on the different unique photodetectors as well. And we focus on the material growth as well as device design and fabrication. I would like to thank our group, entire groups at the USTC, and I'm happy to take any question. Thank you for your attention.
Right. Thank you. Questions?
Okay, maybe I go the first. Sorry, Chris. Yeah. Very nice work idea. Yeah, my question is about the mass production. Is that possible, to make a mass production for you?
Thanks, Professor Zhang. And actually, we recently collaborated with a local manufacturer at Hefei, and we are now raising a lot of funds to manufacture these micro LED structures for mass production. And because this, from our lab, we have demonstrated such high efficient LED, and this can be integrated into a lot of daily life. For example, in the for curing those right now the COVID-19, right? And it's a very popular technology, and it's convenient and efficient. And so I believe this technology has a very bright future.
I just have a quick question. You showed internal quantum efficiencies of 92%, which is indeed incredibly high. Of those structures, what were the external quantum efficiencies?
External quantum efficiency, right?
Yeah, because when you have an internal quantum efficiency that's super high, you must still be able to create a device you can get them all out.
Exactly. Thanks for your question.
You need still high external quantum efficiency.
Actually, yeah. So internal quantum efficiency is one parameter here. If we get, for example, 90 nearly to 1, right? Internal quantum efficiency. But the problem is how we are able to extract the light out of the device as well. So what we propose here in the end, in the second part, you see, we increase this light output power by this method, hybrid sapphire. Meanwhile, we integrate this device this device with a detector here. This is one of the highest wall plug efficiency. This wall plug efficiency is a combination of internal quantum efficiency, which is almost close to 1, plus the light extraction efficiency. But if we divide the internal quantum efficiency to, for example, 90%, and the light extraction efficiency is around 25%, but still low. Compared with blue LED, we need light extraction efficiency to as far as go beyond 50 or more than 60. Then we can compare our UV LED performance with the blue LED performance, but we are still working on that.
Okay, thanks.
Thank you. Miso, thank you very much.
Okay, thank you. So our next speaker. Okay, thank you. Our next speaker is already here, Professor Marisa Westler from the University of Texas, San Antonio. And she'll be sharing her research with the title of Engineered Nanogels as a Synthetic Biomarker Receptors Towards. This is yours.
Thank you, Miso, for the introduction, and thank you of the work that I've been doing, as well as my group at the University of Texas at San Antonio. So that I wanted to share with you that we're starting with is autoimmune diseases. And the reason for this being is that it takes approximately 10 years to reach a conclusive diagnosis. And these diseases currently have no cure, which is very, very devastating. So the disease that we're focusing on is Sjogren syndrome, which is a chronic systemic autoimmune disease. It is prevalent all over the world, but in the United States, approximately 4 million Americans have this disease. And with autoimmune diseases, it is actually common that patients have more than one autoimmune disease at the same time. So with Sjogren syndrome specifically, many patients often have rheumatoid arthritis as well. And with autoimmune diseases in general, many women are more affected than men. With Sjogren syndrome, 90% of the patients with this disease are actually female. And so the major sign and symptom with this disease is dry eye and dry mouth, which is quite vague. It can be a symptom that is associated with many other diseases, side effect of medications, which you can imagine that makes for a difficult diagnosis, which often leads to why it's often delayed over time. So it's characterized by lymphocytic infiltration of the exocrine glands, resulting in the salivary and lacrimal glands, resulting in the major symptoms of dry eye and dry mouth. In order to reach a conclusive diagnosis, though, the physicians must test for B-cell hyperactivity, which are the hallmark autoantibodies of Rho-SSA and LASSB. So in order to overcome some of the challenges which are associated with diagnosing this disease, we must identify first a set of candidate biomarkers for Sjogren syndrome. And so we have listed here a set of biomarkers that are molecular indicators of various aspects of the disease. So we have molecular indicators of lacrimal gland and salivary gland hypofunction, macrophage infiltration, and lymphocytic infiltration, either T cells or B cells. These biomarkers range in molecular weight as well as isoelectric point, and they are present in either tears or saliva, again, with these dry eye and dry mouth being the major symptoms associated with the disease. With Sjogren syndrome specifically, it can take anywhere from 6 to 10 years, again, to reach a conclusive diagnosis. And it is important that we diagnose these diseases at the early stages. Because there's no cure, we can only treat the symptoms. And we must treat these symptoms early, because if they're not treated early, there could be damage that's taking place. And the later that we treat these, any damage that has occurred up to this point can no longer be reversed. So the goal of our work is to develop a screening or diagnostic assay that can detect biomarkers, not of just autoimmune diseases right now. This is what we're currently focusing on, but many other chronic diseases that could suggest the presence of these diseases at much early stages to reduce any damage that's taking place, to get better care for patients all over the world. So there are two major components of biosensors. That's a recognition agent and a signal transducing agent. Our biosensing approach uses gold nanoshells as our signal transducing agent due to the localized surface plasmon resonance that it's exhibited by these nanomaterials. So when light of a larger wavelength than the size of these gold nanoshells hits the surface of the nanoshells, electrons oscillate at the surface. And then when we use UV visible spectroscopy, we can observe a spectrum that looks something like this for the gold nanoshells that we use for our biosensor here. So we use spherical gold nanoshells, and then we can look at the maximum localized surface plasmon resonance wavelength, or max LSPR, which would be indicative of this point here. And whenever the gold nanoshells are sensitive to changes in the local refractive index, so when we modify the surface of this, we can observe a red shift or a change to the right, and we can look at changes in either surface properties that we can use to detect changes in sensitivity to different biomarkers. And so that's our signal transducing element, but our recognition element that we use are hydrogels, specifically polymeric hydrogels. And the reason for this being is that they're highly tunable. So we can custom make these hydrogels to interact with whatever biomarkers that we are specifically interested in. So we can incorporate different monomers based off charge that can interact with different proteins based off isoelectric point. We can also incorporate different monomers that can bind to different properties on the proteins, which I'll go into a little bit later. Another aspect of using hydrogels as the recognition agent is that this reduces costs. So as an alternative to antibodies that require specific synthesis methods, the hydrogel is actually quite simple to synthesize, and it doesn't require use of a cold chain, so we can just keep these at room temperature for improved stability. And so again, because these gold nanoshells are sensitive to changes in refractive index, we can modify the surface of the gold nanoshell with a hydrogel coating. We observed a red shift change in the maximum LSPR wavelength, and then we get this, which we'll go into later, but this will be a delta or change in the maximum localized surface plasmon resonance wavelength. And so the first part of this work was to investigate the use of these hydrogel materials as protein biomarker receptors. So we identified a set of protein biomarkers that are tier protein receptors and to interact with our hydrogels. And so our hydrogel nanoparticles are primarily based on N-isopropyl acrylamide, or NiPAM. They're copolymerized with methacrylic acid, which is our anionic component. So we're synthesizing negatively charged nanoparticles. We have incorporated a custom aldehyde functional oligoethyl glycol acrylate, or ALOEGA monomer. This specific monomer can form covalent bonds with solvent accessible lysine residues that are present on the surface of proteins. So this methacrylic acid component, which makes our nanoparticles anionic, can bind to high isoelectric point proteins, which are net positively charged at, we did this experiment in phosphate buffered saline at pH 7.4. So the high isoelectric point proteins are net positively charged, thus interacting with the anionic nanoparticles. And we hypothesized that incorporating this covalent monomer, or this monomer that's able to form covalent bonds with solvent accessible lysine residues, would thus enhance that interaction in addition to the electrostatic interactions. And so in the bottom here, we have 3 graphs. The acronyms here, NM refers to our polynipam comethacrylic acid, NMA refers to the polynipam comethacrylic acid co-ALOEGA. The subscripts refer to the ratio of the methacrylic acid to ALOEGA that was incorporated into the polymerization. And the graphs I'm showing here are the absorption capacity, which is a measure of the amount of protein that can bind per mass of nanogel. And so what we observed here is that we observed an increase in absorption capacity of high isoelectric point proteins. So the blue, red, and purple lines here that you see across all these graphs refer to our high isoelectric point proteins tested, lysozyme, lactoferrin, and IgG. Beta-lactoglobulin and albumin are low isoelectric point proteins, or they are net positive, or net anionic in charge. So we have charge repulsion, and thus really no interaction with any of our nanogels tested. As we increase our aldehyde component in our hydrogel, we start to see some separation in the absorption capacity here. However, what we noticed in this experiment is that these interactions across all these nanogels tested are primarily driven by electrostatic interactions. So we observed the highest absorption capacities only in our control, which was our 9-PAM methacrylic acid. So even without the addition of our covalent monomer incorporated into our hydrogels. And so this was interesting to us because at the bulk nanogel level, we only observed the effects of electrostatic interaction. So this was quite interesting to us at this point. And so we moved on to investigate the use of our signal transducing agent when we incorporated our gold nanoshells into this mix. So we have our gold nanoshell as a core here. We modify the surface with a methacrylate group to serve as an anchor of which our polymer can then be polymerized from the surface. So we use that same polymerization scheme in the slide that I showed previously that polymerizes from the methacrylate group on the surface. So here's our modified gold nanoshell. We use the same monomers as described previously, and we get these kind of flower-like structures on the surface. And we're using the same formulations as described previously. Our control is 9-PAM methacrylic acid, and then our 9-PAM methacrylic acid co-aloe-vega. Again, the subscripts refer to the ratio of methacrylic acid to aloe-vega into the formulation. So again, we did this in phosphate buffered saline at pH 7.4. This time, this is a solution-based sensor. So we did this in a 384 well plate. We can vary our formulation of the gold nanoshells going down the well plate, and across we can vary the protein concentration in our buffer. This experiment is done with proteins individually. So we're looking at each protein by itself. We're doing 4 proteins here, 2 high isoelectric point proteins, lysozyme and lactoferrin, that are present in tiers. But again, this is just protein and buffer alone, and 2 low isoelectric point proteins, beta-lactoglobulin and IgA. Again, they vary in isoelectric point. And what we hypothesize that we would observe is as protein binds to the surface, again, because the gold nanoshells are sensitive to changes in the local, in the refractive index, we would observe a red shift. And as more protein binds to the surface, we would see a shift to the right. And then we can determine this change in the maximum localized surface plasmon resonance, which you'll see in these graphs here. And so what we observed in this first graph here is the delta localized surface plasmon resonance as a function of lysozyme concentration. Our black bars are our control, just the 9-PAM methacrylic acid, and then our gray and our white bars indicate our increasing component of our covalent monomer incorporated into the polymerization scheme. And so we observe concentration-dependent increases in the maximum localized surface plasmon resonance wavelength with increasing concentrations of lysozyme. We observe statistically significant increases in the concentration of lysozyme at concentrations greater than 20 micrograms per mil. However, we observed no changes when we had our 2 formulations that contain the aldehyde component for lysozyme. When we tested with lactoferrin, this is when we start to see changes between the 2 formulations that contained our aldehyde component. And when we look at lactoferrin has more solvent accessible lysines. And so when we incorporate our signal transducing agent, this is when we start to see the differences in the use of our monomer that's able to form covalent bonds with our solvent accessible lysine. So while we didn't see that at the nanogel level, we see that when we add the gold nanoshell, and this is because once we add our gold into our sensor, that significantly increases the sensitivity of this sensor. When we test this with our low isoelectric point proteins, we observe little to no binding with our low isoelectric point proteins. When we translate this, of course, that's what we want to do, is to translate this to a clinical outcome. We did this with commercially available pooled human tiers. And how we did this study is we determined the concentration of lysozyme and lactoferrin using an ELISA kit. And we performed serial dilutions of the commercially available tiers based off of these concentrations detected by the ELISA. Did the same study, but now we're doing a multiplex study by testing these two proteins at the same time. And what we found here was, again, concentration dependent increases in the localized surface plasmon resonance as protein concentration increases. But what was interesting here is that while in our nanogel, we only observed effects of electrostatic interaction, when we add our gold nanoshells and when we looked at proteins alone, we observed that our aldehyde component takes over. But when we look at our tier sample, we need both our anionic material, but also the covalent monomer. And so our second formulation actually sticks out the most here. So we need both of them in our sensor developed. So this was actually fantastic data that we were able to collect, and something that we were able, we hope to translate and do some future clinical studies. And these concentrations are clinically relevant as well, which is extremely great. So to translate this in an idealized scenario, we need to translate to idealized scenario. We need to make assumptions. So we would assume that lysozyme and lactoferrin have a mass ratio of 1:1. We did a dilution in this case. We diluted our tier sample at a 20-fold dilution. So if we then multiply our dilutions by 20, it would look something like this. A shift change of about 25 or so would result in a concentration of 1.5 mg per mil, and that would associate a patient sample with dry eye. And then this, which would be this blue region here. This orange region could be one in the middle, could suggest further testing. And a concentration range of 3 mg per mil, this green region here would be non-dry eye, and that patient is healthy and fine. So this is something how we would see this moving forward in the clinic. And so again, we were able to develop this biosensor to detect changes in protein concentration. We observed that both an anionic and covalent monomer was able to be used for this application. And based on what we were able to do, we could detect the dilution of tiers at clinically relevant concentrations that correspond to that of dry eye and could be used for clinical translation. So again, this is just one aspect of the work that I'm doing in my group. We also have a few other projects going on. This is just to show you briefly, but I couldn't do this without the support of the students and trainees I've been working with. So I would like to thank them, as well as the different funding sources that have supported this work, and all of you for your attention. I'd be happy to take any questions.
Okay, thank you very much. So time for questions.
Yeah, that's a very impressive work. My question to you is, to avoid a non-specific binding, or false positive situations, what are the strategies and approaches that you foresee?
Right, that's a great question. So the main aspect that we need to do with this sensor is train them with actual clinical samples. So what we did in the study was a commercially available pooled tier sample. And so that was like a starting point to get a proof of concept. But in order to translate this, we actually need to do a clinical sample and correlate those shift changes to what a healthy patient would be to a diseased patient, and what anything in between, and get that pattern to correspond to that. And only with that could we then correlate that to false positive, false negatives, things like that.
Okay, we can take probably one more question.
Sure, I can jump in. So when you're coding your particles, do you know how much coverage you have on those particles, or do you have any way of looking at that?
Yeah, we haven't looked at the details of actually how much coverage. We've only really looked at the size of the surface, but that is something that we've been trying to look at, how to look at more specifically what are the ratios and how can we quantify those specific binding sites in the numbers. But that's something that we're trying to look into.
Okay, thank you.
Okay, That's great. So
Thank
time's
you.
up. So we would like to move on. Thank you, Marissa.
Thank
Okay,
you.
Martin.
Let me stop here.
Okay, so our next speaker is Swingarm. She comes to us from University of Michigan, Ann Arbor, Chemical Engineering Department. She's going to be talking to us about low-dimensional quantum emitters and future perspectives in wearable optoelectronics. Shwen?
Great. Let me just get it set up. All right. Thank you, Martin, for your kind introduction. I have really enjoyed all the talk today, and I want to thank the organizing committee for providing such great opportunity for us to share the work, particularly to this group of very finest researchers from around the world. So today, we have heard several wonderful talks about light because it has been important to humanity, so important to humanity. And we have evolved not only to love light, but also to need light. Over the hundreds years of, okay, it's not working. Over the hundreds of thousand years, mankind has learned to generate light from campfire, which kept darkness away, from candle and oil lamps, which enable vision at night, and from light bulbs and light emission diodes, which are more efficient, controllable, brighter, and sharper. But that's not all. What is more fascinating about light to me is that its function has already moving beyond lighting. For example, visible light emission diode has enabled display and changed our life totally. In addition, they can be used as to treat jaundice disease in the newborns, or to monitor the blood oxygen level or the heart rate through your smartwatches. Light has also been used in lithography, face recognition, cancer treatment, and more. So you may ask, where does the light come from? There are many materials that can emit light. Colloidal quantum dots is one of the most exciting ones, in my opinion. They're tiny crystals of different shapes, and their size is 100,000 times smaller than a grain of table salt. More importantly, they can be synthesized in liquid and processed into solid from solution. That makes their large area and low cost of fabrication possible. In addition, because of their small size, they exhibit quantum confinement effect, meaning that their electronic band gap can be continuously tuned by simply changing their size. Therefore, as emitter, their color can be tuned accordingly. Another important benefit of the quantum confinement effect is that the emission spectrum are very narrow, and that narrowness translates to, when they're in display, will translate to the sharp color. For example, compared to the OLED, quantum dot display can render images much more colorfully and realistically. That quality of image also reflected in their price tag if you shop around Best Buy and check out this quantum dot TV. So clearly, quantum dots embody the excellent optical properties and are considered as the next generation of light emitters. However, there are also challenges that fundamentally limit their application. For example, due to the relatively large specific surface area, defects tend to form at the surface of these nanocrystals, which compromise their optical performance. And ligands and shells actually are often used to passivate or remove these electronic defects. However, the existence of these ligands leads to poor electronic transport property. Lastly, quantum dot thin films are mechanically brittle. They tend to form cracks when being bended or stretched. That limits their application in wearable and biointegrated electronics. I think it's safe to say that understanding and resolving any of this issue has been difficult, and the attempt to solve multiple problems at a time is utterly challenging. So in the remaining of this talk, I will first review the light generation in semiconductors, and then we will look at a new strategy to address both surface passivation and electronic transport simultaneously. In the end, we will discuss a new set of challenges to achieve wearable electronics, wearable optoelectronics, and our pathway to solve them. Let's look at how light is generated first. So when charge carrier is generated in a semiconductor, they can move around. And if a pair of electron and hole meet each other and recombine, they can radiate a photon. Light is therefore generated. Yet semiconductors are not perfect. In fact, they contain considerable amount of defects most of the time. So when carriers travels to meet these defects, they will be trapped and recombine without generating light. And the efficiency of light generation in LED can be simplified as the ratio of the radiative recombination events over the total recombination events. As mentioned earlier, quantum dots tend to form traps on their surface. And in order to maximize the light emission, we need to get rid of them. So insulating ligands and thick shells has been used in the past to coordinate with the surface atom of the quantum dots so that to remove these defects. However, the insulating nature of these long ligands and thick shell compromise the charge transport, meaning that higher voltage and higher power will be needed to drive the same amount of current through the device. Well, you may think, why don't we use shorter ligands or thinner shell? Indeed, that is a great idea to promote a carrier transport. However, the surface defect passivation is no longer sufficient and the defect will start to form again. So as you can see, both passivation and transport are important in quantum dot electronics, but there seems always a trade-off between them. So you have to ask, can we achieve both passivation and transport simultaneously? This is an important question. So if we're allowed to dream any possible strategy to achieve this goal, how about if we can embed quantum dots in an epitaxially aligned matrix so that which also have high carrier mobility? Well, in that way, excellent surface passivation can be achieved through the atomically aligned lattice, and carrier transport can be introduced from this magic matrix to the dots. Can we design and build such system realistically? So we start to test this idea on lead sulfide quantum dots, and they're known as very efficient near-infrared light emitter. And after being synthesized in solution, two sets of facets of lead sulfide are commonly observed, which is 001 and 110. So while we're looking for a new passivation matrix for lead sulfide dots, we found that the crystal structure of metal halide perovskite surprisingly matches well with these dots. In addition, perovskite has been known for their excellent charge transport with high carrier mobility. So it's clear that this material is an ideal candidate to provide surface passivation to the quantum dots and enable excellent electronic transport. So we soon came up with a new synthetic method that successfully grow lead sulfide dots into the perovskite matrix. And then we ask ourselves, all right, they're now together, are these two materials aligned with each other at the atomic level, the way that we imagined? So the TM image on the right show that the crystal fringes of lead sulfide and perovskite, methyl ammonium lead sulfide, lead iodide perovskite particularly, align with each other, although we did observe also certain mismatch at the interface, and that agrees with a lattice mismatch between the lead sulfide and perovskite. So now we confirmed they are aligning with each other. And if that is the case, we would expect to reduce the surface trap and therefore brighter emission. So we looked at their photoluminescence quantum efficiency, and we found that the quantum dots quantum efficiency increased from below 0.01% to around 10%. That is, the brightness of the quantum dots improved by 1,000 times with atomic aligned perovskite matrix. We know that such improvement stems from the epitaxial alignment, because if not, for example, this sodium iodide matrix, if dots is embedded there, the quantum efficiency of quantum dots still remains very low. So we also note that the methyl ammonium lead iodide perovskite still present a 6% of the mismatch with our dots. So, and we can actually further reduce it by changing the chemical composition of perovskite. Particularly, we can change the halide side of the perovskite from pure iodine to the mixture of iodine and bromine so that we can tune their lattice size. And with the improved lattice match or decrease the mismatch between dots and perovskite, we did observe the quantum efficiency of quantum dots can be further improved from around 10% to 24%. And that represented the highest PL quantum efficiency of near-infrared dots at the time of this work. So inspired by this excellent emission property and high carrier transport efficiency, we moved forward to design and fabricate a near-infrared light emission diode using dancing perovskite. And the electron and hole, in this case, will be injected from top and bottom electrodes and to perovskite, this semi-transparent matrix here. And then they will be transported within perovskite to the quantum dots because there's a special type 1 band alignment. And eventually, these carrier will arrive at the dots where they recombine and emit light. So we found because of the superior optical and electronic property, the external quantum efficiency of our quantum dot LED reached a record high of 5.2%. And that is 25 times higher improvement actually compared to the quantum dots with just ligands. So that means to generate the same amount of near-infrared light, we not only need 1/25th amount of the energy. And these extremely efficient near-infrared LED can facilitate various applications, including night vision, optogenetic therapy, bioimaging, and beyond. To summarize, epitaxial interface between quantum dots and perovskite is a new strategy that allows us to achieve excellent surface passivation and electronic transport simultaneously. On top of that, this type 1 heterojunction also enhances the carrier injection from the perovskite to quantum dots. In other words, if we want to preserve the high optical performance of quantum dots while introducing a new flavor of electronic transport, we need to find the right path to incorporate them. Because if not, you may lose integrity of the dots and you will get, or you will end up with the phase-separated quantum dots and perovskite. And only with a careful design and atomic line interface, you can actually get the best of these two components. So now we have overcome the efficiency of quantum dots LED. What's next? I am always passionate about exploring the new functionality of light, and I strongly believe one interesting direction of the future optoelectronics lies in wearable. Wearable electronics is on the verge of redefining the human-machine interaction in consumer electronics, personalized healthcare, biomedical research, and beyond. To achieve this futuristic functionality, optoelectronic materials and devices need to meet a new set of requirements. They should be soft, thin, and stretchable. However, the mechanical deformability of today's quantum dots is rather concerning. Crack will surely form when we stretch the colloidal quantum dot film. In fact, we recently find actually simply bending the quantum dot thin film will already lead to crack formation and mechanical failure of lead sulfide thin films. So our quantum dot film today are rigid and far from being wearable. So generally speaking, the ratio between the critical strength, energy release rate, and the modulus can be used to evaluate the rigidity of materials. And the rigidity of the quantum dot thin films is very close to those of rigid inorganic crystals and below the flexible organic semiconductors. And great efforts has to be made to move towards the higher end where the soft and stretchable elastomers reside. So in our very recent work, we developed a new class of stretchable quantum dots emitting material by designing a new polymer matrix, which can not only serve as stretchable platform, but also optically, it passivates the surface of the quantum dots and provide electronic transport pathways. Through careful design between stretchable conductive polymer and quantum dots, we can address the three challenges of quantum dots simultaneously. As a result, the quantum dots film can be stretched to 300% strength without the formation of cracks. And we further developed the first intrinsically stretchable quantum dot LED. So the future of optoelectronics is truly exciting, and light in its wearable form will enable powerful tools in healthcare, smart agriculture, soft robotics, and artificial intelligence. This January, I started my own research group at the University of Michigan, and we will address these challenges of mechanical deformability of dots through new material innovation and deep understanding of their mechano-optoelectronic properties. So please keep an eye on us. In the end, I'd like to acknowledge my former supervisors, current students, and funding agencies, and I'll be happy to take any questions.
Right. Questions?
Thank you very much.
Thanks for a nice talk. You have a lot of applications in mind, even bio applications, and one of your slides, even light therapy applications. Surely the lead component is going to be a massive issue in there. So how are you going to address that? Because if you remove the lead, surely your devices will not work anymore.
Yeah, that's a wonderful question. Indeed, I don't think anyone wants to wear lead on their skin or implant them. So so heavy metal free or non-toxic quantum dots is one of the important area in our research too. And the recent development of the near-infrared dots already has some improvement in terms of getting rid of lead. There are indium arsenide dots. There are, well, mercury probably not an improvement. But yeah, so there are silver-based, silver sulfide dots can also deliver very high optical response that without lead. So it's an exciting field, but indeed we need to move further.
Yeah, but the competition will be very stiff because for the applications you propose, there are already existing solutions that are perfectly biocompatible. So how are you going to compete with that?
Well, that's an amazing question.
Be better than already existing solutions?
Oh, that's a good question. I should have mentioned that the alternative, for example, would be organic optoelectronics, which there could be, flexible. However, one major limitation of organic semiconductor is their response in the near-infrared region is rather poor. For example, they are excellent in visible, but in the, let's say, bio window 1 and 2, which is around 950, and another one is 1400 nanometers. Their photoluminescence efficiency, stability are very much lower than the quantum dots, while inorganic nanomaterials excel in the field uniquely. So there is a field that need this particular optical properties that the alternative could not provide.
Okay, thank you.
Nick, quick question.
Yeah, so I guess a related question is how do you address the interface issues? You mentioned about the mechanical part. What are the other conditions or constraints you need to consider?
Well, this is again a very amazing question. So I didn't go into detail into the designing rule of, let's say, dots in polymer, but there are several parameters we should consider as a guideline. For example, as you said, mechanical deformability is one. Also at the interface, how about the surface passivation? For example, the bonding between polymer and dots, how can we achieve the efficient bonding? And also the electronic coupling is another important issue. We can't just embed dots in an elastomer because there would be insulating. How can we control the energy transfer from the polymer to the dots is also another important question. So you're right, there are several issues to consider, and we also propose several guidelines to achieve them simultaneously. And it's not an easy task, but we can solve them actually eventually.
Right. Thank you very much for that talk. I will hand over to Miso.
Okay, thank you, Martin. So our next speaker is the 10th presenter, so Professor Sandra Camarero Espinosa from the University of the Basque Country. And she'll be sharing her talk on the title of Designing Materials as Building Blocks for Life. And Sandra, the stage is yours.
Give me 1 second. Sorry, 1 second. Yeah. So thank you very much, Mr. for the nice introduction, and thank you to the organizers for giving me the opportunity of being here today. So today I would like to show you a little bit of the work that we conduct at BioSmart. We focus on tissue engineering, and this is because we live on an aging society, and our quality of life depends every day more and more in our capability to regenerate damaged or injured tissues. So tissue engineering was first postulated on the early 90s under the concept of isolating cells from the patient, expanding them in vitro, mixing them with a scaffold material, perhaps with some growth factors, and further culturing them, generating a tissue that could be implanted back into the body. 20 years later, with the boom of the 3D printers, this came out at The Economist saying, making a bit of me, a machine that prints organs is coming to the market. So 10 years after this, we are still far away from these printing organs. And this is actually because tissues are hierarchical. They come together, they organize into organs, providing them with a very specific functionality. Now, if we look down to the tissues itself, they are also hierarchical. Cells interact with each other at the nanometric scale, which dictates their fate. They also arrange into different orientations and distributions. They finally combine into multiple layers, which actually provides organs with specific mechanical properties and functions. Now, what we realize is that engineering tissues in vitro is fairly easy. However, making them functional, that is another task. It's very complicated. So there are currently two main approaches to do this. The first one would be defined as form follows function, in which we try to mimic as much as possible this hierarchical structure of the tissue. So we can make cells, host cells, to feel like on the native environment, hoping that they will deposit then a coherent tissue. Now, the second approach would be function follows form, in which we can stimulate externally cells with physical stimuli similar to that they feel in vivo, and then hoping that they will deposit again a coherent tissue. Now, our groups and many others have been mainly focused on this first approach, in which we can control the chemistry and the biochemical composition of the fabricated scaffolds. We can also control the structure of the fibrous material. We can arrange them into multi-layer scaffolds and further control the mechanical properties. So one example of this, where a lot of groups have been working, is controlling this biochemical composition of the scaffolds. And this is important because cells interact with each other via caderins. They also can interact with the extracellular matrix via integrins and further with soluble factors. All of this together dictate the cell fate. However, here it's not important only the biochemical functions that we present to cells, but the spacing at which we do it. So these are mainly sensed by integrins that have a defined lateral spacing. And so it has been shown that if we present biochemical cues to cells on a lateral spacing lower than 44 nanometers, this will interact strongly, forming a strong focal adhesion. However, if we have now our biochemical cues a little further apart, these interactions will become weak. So exploiting this idea, we developed some two-dimensional cell culture platforms that are based on self-assembling copolymers, so we can control the lateral spacing, and we use them to present peptide sequences to cells, hoping that we can now differentiate stem cells into these three very characteristic chondrogenic phenotypes present in articular cartilage. So in order to do so, we selected some peptide sequences characteristic from proteins in the extracellular matrix of cartilage and also from cell-cell interactions. And we presented them to cells on a combinatorial manner. What we notice is that depending on the substrate composition, we will have very different scenarios. So we could have very few cells attached on our substrate. We could have the formation of monolayers, the formation of aggregates, and intermediate states. We further realized that identified 5 different substrate compositions which will drive the spontaneous formation of aggregates by stem cells, which is traditionally sensed as the onset of chondrogenic differentiation. We further analyzed these substrates and we could identify 3 of them that would drive the differentiation of cells towards persistent proliferative and hypertrophic chondrocytes. We were further able to extrapolate these two-dimensional platforms to 3D culture systems by electrospinning, and by simply controlling different spinning parameters, we could also control the type of self-assembly system, which we further used to study these extracellular matrix cell interactions on a 3-dimensional culture space. Now, we would also play a little bit with this concept of controlling the cell distribution and orientation. In this case, we did it with the idea of regenerating antigen cruciate ligament. And this is because it is also a hierarchical structure with cells presenting very distinct phenotypes. And here what we can observe is that on the center of the tissue, we have this wavy structure that becomes more elongated towards the emphasis with bone. So in order to mimic this structure, what we did is we electrospun our polymer into aligned mats on top of thermally shrinkable films that upon exposure to heat will form this wavy structure similar to the one that we find in the native ACL. So what we observe is that this wavy structure had a direct impact on the mechanical properties of the scaffold that now presented these two regions, which is also characteristic of ACL. Not only the mechanical properties were affected, but also the way cells behave when cultured on these scaffolds. So in our wavy scaffolds, they will form aggregates, while this was not the case for the other structures. This also impacted the extracellular matrix deposition, which was abundant, and fibrous in the case of wavy scaffolds. Further analysis of this composition showed that this was very distinct depending on the structure of the substrate for cell culture. Now, on the wavy scaffolds, our cells were able to deposit collagen II and also fibronectin, showing that they have a phenotype that is characteristic of fibrocartilage formation, which we also correlated by PCR analysis. So having formed these different structures and being able to control the cell fate, we extrapolated to three-dimensional scaffolds that we could implant into a rabbit model. So we created aligned scaffolds, wavy scaffolds, and some triphasic scaffolds that really mimic this structure of the ACL, being aligned on the extremes and having a wavy pattern on the center. Now, after 12 weeks of implantation inside the body, what we observed is that aligned scaffolds and also triphasic ones were presenting the formation of an abundant matrix similar to the normal ACL. However, wavy scaffolds and triphasic ones were presenting an abundant collagen matrix that was also aligned similarly to normal ACL. So in these two examples, I show you a little bit how we can indeed control different aspects of tissue formation by controlling these different scales. However, it is clear, or we came to the realization that in order to control all these different parameters of a scaffold, these ones will need to be highly sophisticated. And this complexity is a problem when we want to extrapolate them to an industrial scale, and perhaps some of these parameters get also masked when we implant them into the body, right? So we are getting more and more excited or interested in this other concept of function follows form. And we were looking at remote stimuli that we could apply, right? So we look a little bit at 4D printed scaffolds, which are 3D printed scaffolds that can be actuated externally. We found out that many of these stimulus, or most of these stimulus, are not applicable to an in vivo situation or under physiological conditions. So we thought, what about using ultrasounds, right? Ultrasounds are currently used in the clinic and in many cases to enhance bone formation. So the hypothesis here is that these are pressure waves that will directly act and be sensed by cells that in return will deposit and enhance bone matrix. Now, for this hypothesis to be true, first, we must have a tissue template, and this is not always the case. For example, we have a critical size defect. So we thought maybe we can create now 3D printed scaffolds that respond actively to the ultrasound stimulation, deflecting and translating this deflection to cells, resulting in a mechanical stimulation, right? So we look a little bit to what is out there on the market, so to ultrasound transducers, and we realize that they are made up of an active element that readily vibrates upon application of ultrasound and a baking material that dissipates these waves. So when these two come together, what you get is a pulse and control wave in response to the ultrasound application. And so how can we do that practically? So we look a little bit at the physicochemistry concepts, and we choose two biocompatible and biodegradable materials, PLA and PCl. being one of them amorphous and the other one semi-crystalline. So when we blend them together and we 3D print them, we see that depending on the polymer ratio that we use, this one will phase segregate following a nucleation and growth pattern. However, at a 50-50 composition, we were able to see the formation of these Janus scaffolds, having one phase reach in PLA and the other one reach in PCL. Now, this was homogeneous along the whole entire scaffold and under the same direction. We could further observe this Janus structure not only by SEM and by SEM and TM, but also by polarized microscopy and light scanning microscopy. So we took these Janus scaffolds and we modeled the deflection under the application of different ultrasound waves. And what we observed is that the higher the frequency, the smaller the amplitude of the deflection, right? But what we also observed is that this amplitude of deflection will depend on the material that we were using, so on the mechanical properties of this material. Having PLA the highest deflection, the lowest PCL, and Janus having a behavior in between these two. Now, when we culture cells on top of these materials, what we observe is that the growth pattern, the proliferation, was also dependent on this amplitude of deflection. So at higher amplitude, some of the cells were dying. At a lower amplitudes of deflection, corresponding to the 40 kilohertz, they were proliferating at a faster rate, having the highest proliferation PLA scaffold, followed by Janus, and finally PCL scaffold. So that makes sense, right? This proliferation is related to the amplitude of the deflection. Now, when we look at the position of matrix, we saw that in this case, fibronectin was much higher deposit in the case of Janus scaffolds, and this made us wonder, so if this is not related to the amplitude of the deflection, what it is then? We decided to go back and look at actually how these materials deflect the ultrasounds, and using in this case a nano-indenter, and what we observe is that PLA indeed behave as an active element, vibrating readily upon ultrasound stimulation. PCL scaffolds behave as a baking material, and Janus scaffolds were able to behave as transducers with a pulse wave. So when we use them now for bone formation, we observe that indeed Janus scaffolds have an increased collagen 1 deposition, mineralization, and also show a regulation of characteristic osteogenic markers. Now, we could correlate this particular behavior to the formation of calcium ion channels by PCR and also by fluorescence light microscopy. And furthermore, when we chemically block these calcium ion channels, we didn't observe anymore this upregulation of osteogenic markers. So with this, I hope that I show you that we don't have only the traditional form follows function approach, but that this other approach is gaining more and more interest, or at least for us. And I would like to finish, and I would like to thank all past and present collaborators, our current group, the funding, and of course, all of you for your attention. Thank you.
Perfect timing. Thank you very much. And time for questions.
I can jump in. A quick question, very quick question. In your 4D printing, do you see any?
Okay, go ahead. Thank you. Oh, Martin. Yeah.
Do you see any collagen alignment due to the vibration?
Yeah, that's a very good question. We didn't observe it. We didn't actually pay attention to it. I don't know if this would be related directly to the ultrasound exposure or rather the pattern of the 3D printing, but this is something that would be worth investigating. What we do know is that we can tune the ultrasound waves to generate different patterns. So this actually could be something very interesting to look at. Thank you.
Yeah, on follow up to that, because the usefulness of the tissue depends on whether the collagen is organized or not, right? If you want to build a cartridge, for example, you can get collagen type 1 or 2, but if you don't know its order, then you can implant it. And if you put it in the bone and it organizes the wrong way, then actually you get scarring, you don't get bone healing. It can become a barrier.
Yes, thank you. This is a very, very interesting point. So one of the projects that we are working on at the moment is actually related to that, is related to playing with the structure of the 3D printed materials. So we can control this ultrasound deflection, not only in amplitude, but also in directionality through our 3D printed scaffold, or 4D printed scaffold in this case. So I hope that in the near future, I can give you a more precise response to that. Thank you.
Thank you.
It's a very good point, yes, indeed.
All right.
Hey, Nick, would you want to ask questions?
Yes, yeah, I would like to follow up on the ultrasound enhanced stimulation. I understand that it is already an emerging need to qualify the tissue scaffold for cell expansion, cell manufacturing, and I'm wondering how would you qualify the use of tissue scaffold combined with ultrasound? What will be the say metrics to monitor, for example, the side effects and the other safety issues?
Yeah, thank you for the question. This is also very interesting. And actually, I gave an example of exploitation of ultrasounds clinically, that is for bone formation, but there are plenty of other applications. There is for imaging, but it's also used for tissue ablation. So you can use it for tissue generation, but also for tissue ablation. And this is at the moment relatively well defined, and it actually depends on the intensity of the wave and the frequency of this one. So we will always try to move, and in this case, we are actually on the safe frequency and amplitude range that we can use before generating any tissue damage. One of the main issues that I would see here is the transportation of these waves until the place of injury, right? Because our experiments are in vitro and everything is very nice, but when you put it in the body, there could be certain attenuation. So we will need to work on that, and we will need to look it up directly in vivo. Adjust the parameters to reach our scaffolds with the same frequency and intensity that we were doing it in vitro, and also analyze the surrounding tissue. Yeah, to of course evaluate which are the effects to that healthy tissue that is in there.
Okay, we're in a good shape to move on. So thank you so much, Sandra and Martin. It's your turn again.
Okay. So our next speaker is going to be Jessica Tucker. Jessica comes to us from Mount Kenya University in Kenya. That's in East Africa. And he's going to be telling us about development of point of care and game diagnostics for Africa. Jesse?
Thank you very much, Martin. Can you see my presentation?
Yep.
Thank you very much. Yeah. So I'll be talking about development of highly sensitive field deployable molecular assays for malaria elimination. Our lab, my lab, works on several other types of assays, but today I'm going to talk about the malaria story. So malaria is an important infectious disease with over 240 million infections and 625,000 deaths in 2020. And as you can see here, there is a decreasing incidence of malaria, but again, there is a big challenge with
Yes, you are muted.
Good. You can hear me now?
Yep.
Yes.
Yep.
Good. Thank you.
So now your slides are gone.
Back.
Good. So thank you very much. Yeah, so there's a big problem with the symptomatic infections which are increasing, and this is a big challenge. our own studies have shown that asymptomatic infections is a big problem in Africa. So one major challenge is how do we diagnose these asymptomatic infections? So here there are several challenges. There are solutions to these asymptomatic infections. One of which is, of course, mass drug administration and MSAT. So mass drug administration is a great strategy in eliminating these infections in the community. However, this may lead to resistance, and the WHO recommends specific use cases for this. The other strategy is, of course, mass screening and treatment. And one of the challenges with this is that we need highly sensitive tests that will be able to, detect these infections and then enable treatment. So, good. So the WHO has identified the ideal tool. The ideal diagnostic tool is proposed to be one that is highly sensitive, affordable, and simple enough to be operated in the field. So this tool will really be the first step towards elimination of malaria, because it will enable this mass screening and testing, and then treatment. So good. So the ideal test has to meet these assured criteria, which is must be affordable, sensitive, specific, user-friendly, robust and rapid, as well as being equipment-free and deliverable to those people who need it. However, for us to really achieve this, we need the right assay. So the right assay is at the heart of achieving these assured criteria. So current strategies, including microscopy and rapid diagnostic tests, have their own challenges, as you can see here. For microscopy, you are only able to detect 50 to 100 parasites per microliter, this being the limit of detection. And as you shall see, this is really limiting, because for asymptomatic infections, you need a test that can diagnose 1 to 10 parasites per microliter. For the rapid diagnostic tests, they are great. However, recent deletions in the target genes, including the PF, LDH, or the histidine-rich protein 2 antigens, has made these tests not sensitive. And there are reports in Kenya, Eritrea, Ethiopia, and other places which show that many of these tests are missing infections, propagating the spread of the disease in the community. So there's a major constraint here that our group now aims to address using new strategies. So one of the strategies that could be used is, of course, use of PCR methods to improve upon current diagnostics, as you can see here. But the challenge with these PCR methods is that you need big machinery, you need cold storage, you need to prepare this to sample process. And of course, this brings challenges with the need for other reagents and so on. And again, as you know, the thermocyclers are expensive equipment, they need electricity, and therefore they may not be deployable. They may not be field deployable to those places that need them. And so our group is working on a new strategy. Here I refer to it as identical multi-repeat sequences as a strategy that I'm going to share the data with you for today. So traditional genome mining strategies, as you can see on the left, rely on you aligning target, aligning gene regions, and then using set primers to amplify repeats of these genes or regions, and then being able to visualize this. But our new strategy here uses a deeper way, where you're able to amplify or to identify multiple regions in the genome, which then yield more amplicons. Okay, and then this way you have a high amplicon yield that increases the sensitivity of the test. So using the same primer set, forward and reverse, you're able to amplify more genetic regions and then have a higher yield that you can then visualize using a number of strategies. So this just illustrates how this works. So if you look on this on the left, these are the 14 chromosomes in the Plasmodium falciparum genome, and as you can see, these new sets of primers, the identical multi-repeat sequences, are able to identify multiple regions in the genome, in the whole genome. And when you put this on a gel, you can see that for the IMRS strategy here, you're ending up with multiple yields, multiple amplicons of differing sizes, okay, through being amplified, because this is happening throughout the genome. While if you compare with the conventional 18S RNA, you end up with one, amplicon, at one position. This, which is, if you look at both planes, you can see that with the IMRS, you end up with a lot of yield that is able to, of course, increase the sensitivity. And from this strategy, we have demonstrated that the IMRS strategy is 100 times better or more sensitive compared to the 18S RNA conventional strategy. So this is a probit analysis for the lower limit of detection using the IMRS compared with the 18S. So if you look at the IMRS, you end up with a higher probability of achieving lower yields over time, and this really enables you to have a shorter, experiment time, and equally that's more sensitive. And then if you consider that in the field you really want a test that is able to be demonstrated, to be able to be read within a short time, then you see that the IMRS provides this required test. So, however, if you're doing IMRS using the PCR strategy, then that may not really yield much, because it's the same. You end up with the same problems as the conventional PCR methods. So we need to convert this IMRS strategy into isothermal IMRS, so that you are able to use a single temperature and be able to amplify multiple regions, and then demonstrate this using an easy-to-use visualization strategy, such as the lateral flow assay. So we went ahead and compared ISO-IMRS with 18S RNA PCR. And as you can see here, even with 18S RNA using PCR, the ISO-IMRS strategy does better. And you're able to demonstrate 1 parasite per microliter, which is better than the 18S RNA. So, and when you look at the threshold time for the ISO-IMRS, you can see that in a short time, within even below 20 minutes, you really have you can be able to demonstrate good concentration or even visualization. So, but again, we needed to go ahead and characterize this ISO-IMRS strategy, whether what we are seeing, the bands we are seeing, are really what was predicted in the bioinformatic in the silico algorithm. So here it shows that exactly the bands you see, they match, okay, with the NGS sequencing alignment to genome of the predicted, as predicted by the algorithm. So, but again, even after you amplify you have your amplicons, you need to visualize them, so remember, you're talking about field deployability. So here we have a visual readout that is enabled by doing it on a lateral flow. So classically in the lateral flow, you really want to end up with a test that is able to have a test line and a control line. And so how do we do this? Of course, we just incorporating farm label primers and both intact DUTPs into the amplification reaction. You can be able to then put this on the sample pad, and through capillary reaction, you'll be able to demonstrate this in the test line if you have a positive sample, and of course a control line to show the validity of the test. So we have done this, and we demonstrated that using the isothermal IMRS strategy, you can amplify multiple regions, and then you can go ahead and visualize this using a lateral flow assay, and you're able to detect less than 10 parasites per microliter, which is really in the range of the asymptomatic malaria, which of course provides this infectious reservoir in the community, from which the mosquito picks gametocytes and then continues to transmit the malaria in the community, affecting the most vulnerable members of the community. So here, this strategy then, from the lab, we needed to validate this using clinical samples. So we proceeded, and so we got matched blood and saliva samples, and we showed that the P-falciparum iso-IMRS was really able to identify 9 out of 10 of the PCR positive samples. And when you look at the same for matched saliva samples, we showed that the assay was successful with the non-invasive samples, because remember in MSAT, in mass screening and treatment programs, you do not want to end up with a situation where members of the community do not want to cooperate because you're going to prick them. You want to have a test that is non-invasive, that allows them to give you a sample without resistance. So getting a blood sample is not as friendly as getting a saliva sample. So showing that the iso-IMRS, because of the higher sensitivity, you are able to pick this DNA and show whether people have infections, is a step in building, in driving towards field deployability. So in summary, the malaria iso-IMRS assay has high sensitivity and specificity, as we've shown. And currently we are at early stages of clinical trial in Western Kenya for field create strategies on how to make this test the test of choice for asymptomatic malaria in endemic countries. Thank you very much. I'd like to thank to acknowledge my members of our group and our collaborators, and of course the funders. Thank you.
Thank you very much. Time for questions.
Okay, great. Yeah, Jesse, appreciate your sharing the results of this, detection. I have a question is for you, provide this technique of this test to the kind of the users. Yeah, they can use it as it is, or they need some different training.
Yeah, so the strategy really is based on the LAMP assay strategy. So using lyophilized samples, the training requirement is minimal. A few hours of training should be really what you need for people to be able to easily use this test.
Okay, great. That's my question is, if they don't need, further trainings, that means, your detections, the samples was really kind of original, you didn't do any treatment about that. So that asks for the high sensitivity.
Yes, yeah.
Okay, thank you.
Mm-hmm.
So I have a quick question. How does this test strip function under different temperature and humidity? Because across the continent of Africa, these things could be vary pretty dramatically.
Yeah, exactly. So this is a very nice question. So currently we have lab data that shows the longevity of the test in the lab. However, as I said, we are now going to the field to see, because as you said, the field exposes you to different conditions. You have different humidity, temperatures, dust, and so on. So we would like to, over time, see how the test performs in the field, in the real world, not just in the lab.
Okay, thanks.
Maybe I have only one quick question because I'm really curious about it, actually. So in the beginning, you mentioned the cost is very important. So I was wondering if you could make it cheap enough. And does your method need refrigerators or not? That is also an important point.
Yeah, sure. This is important. So let me start with the last question first. So of course, we know that enzymes and buffers need refrigeration in their normal state. However, we are using lyophilized reagents. So once we lyophilize and put at the bottom of the tube, that makes it easy to use in the field, because you no longer need refrigeration. And then remember, once the reaction happens in the field at an isothermal, let's say 65 degrees Celsius, then you just transfer to the lateral flow assay, and then you just visualize, you read out. So on that, the lyophilization helps with that. Then the cost, the issue of cost is, of course, during the development stage, we may not really be cost efficient at this point, but we anticipate with scaling to really be able to go sub for $3 per test.
Yeah, thank you.
Thank you. So I think because of time, let's hand over to Miso for our last candidate.
Okay, so we have our last speaker of today, last but not least. So Professor Fan Wang from the University of Technology, Sydney, and he's going to share his research with the title of lanthanide doped nanoparticles for biophotonic applications. Fan, the stage is yours.
Yeah, I'm here. Can you guys see my slide? Oh, good.
Yes, would you want to switch to the full screen?
Yeah, is that okay now?
It didn't work yet. I think.
Okay, now it's work. Yeah, Miso.
Okay, cool.
Now
Yeah, thanks, Miso, for the introduction. And also thanks for the communities like me to join this wonderful event. So I know you're probably really tired, so I'm gonna try to make my presentation more interesting. So today I'm gonna talking about the use of lanthanide doped nanoparticle for biophotonics application. So biophotonics means using the photonics technology to deal with the biological problem. And you may think that we already have tweezer and a knife to deal with the biological sample. Why we still need to use the photonics technology? The answer is simply because we want to deal with a smaller size of samples, like single cell biomolecules and also organelles. So to achieve this one, we actually need a smallest tweezer and a smallest knife, enable us to see, to touch, and to feel the nanoscale world. And then we can have much better understanding what's the working function of single cell and also those kind of biomolecules. So that is photonics. And that is linked to three of my research area, my group. So one is the super resolution imaging, one is the optical tweezer, another one is the single particle tracking and sensing. So because of time limitation, so I want to spend majority time introduce the super wide and spend little time in other two. So super resolution imaging is one type of the optical microscopy. For the conventional optical microscopy, you actually couldn't see the features clearly below 200 nanometer because of the diffraction limitation. And from 2014, this three smart guy developed a super resolution technology. And then for the first time, you can see the features below 200 nanometer clearly. And then we have much better of understanding what's the fundamental of life. We know how the nanomedicine works. So there already have different type of super resolution technology, just like different game characters, like good at different things. For example, the static is good at the resolution, but need high power, so bad biocompatibility. And the storm have really good biocompatibility resolution, but it's a little bit slow. And the structured illumination microscopy, especially nonlinear structured illumination microscopy, is really good. But all of them have a common limitation, which is working depth. You always can see like superrise on single cell, but usually you couldn't see some super resolution through really thick deep tissue, even for some living animal. So that is a limitation. And that is because the tissue actually also absorbs the visible light. So unfortunately, currently most of the available super resolution imaging is on the visible light, so therefore have limited penetration depth. The solution can be really easy, just shift all the working wavelengths to the biological window, and then you can solve the problem. But the challenge is like, how can we move this working wavelengths? Because as you know, also Stephen also mentioned, actually for the near infrared dye and for another probe, it's not that efficient. So our solution is use this kind of up motion nanoparticle. It's kind of nanocrystal, so you can change the different size, and you actually can dope the rare earth element inside this single nanocrystal, and the lanthanide ions can be the sensitizer to absorb the near infrared light and then transfer the energy to the activator or the emitter for the visible light and near infrared light emission. And if you look at the energy level of the emitter, for example, the thulium here, so it's got many energy level, and the carriers actually can go up to the different level by absorb different several time of energy. So just like catch on some ladder from bottom to up, so easier to build up the energy to the higher level, gives the really high level emission come out. And compared to 2-photon absorption and 3-photon absorption, because it's got the multi-energy level, real energy level here, so it's much more efficient. And if you look at the rate equation on different energy level, it's really, really interesting. And it's actually fantastic for us because we have so much freedom for us to play. For example, if you're changing the doping concentration, we can tune it with the cross-relaxation effect. We can make it like super linear and also saturation. And especially for different energy band, the response is also different. So by engineering this kind of optical response, we can achieve different like super resolution technology. So for us, this near infrared probe is just like a really sharp weapon. And when we equip this one with different super technology, we can substantially increase this working depth. And now the challenge comes to how can we use the upward version to achieve the superrise. So the first work to use a up conversion to achieve superrise is based on the cross-relaxation. And if you have like excitation laser, you're going to build up the population inversion in one of the intermediate level. And if you're shining another laser at the same time, and then you're pretty much going to trigger all the carry off. And in other words, you just turn off the emission. So by using this concept, we can directly adopt the STAT technology to do the superrise. So you use one of the laser do the excitation, and you use another donut beam to like eraser, just clean up the emission surrounding by this hole, and then you just have like emission come out from the middle hole. And using this one, currently we achieved 90 nanometer, and you see what you're seeing here is individual nanoparticle, and this is inside a single cell. But for this principle, for this technology, the emissions are still 455, so which is visible, have really limited penetration depth. So therefore, we developed another technology. So that is based on the saturation of the photo response. So over here, we use the 800 nanometer because it's right inside the biological window. And for that case, if you use a Gaussian beam as the, if we use a donut beam as the excitation, and then your emission gonna be the donut as well. But because of this saturation, if we further increase power, the hole in the middle will be smaller and smaller. And just add up to about like 10 milliwatt, actually your hole will go beyond the diffraction limitation. So you have a tiny bit hole in the middle. So we use this technology to watching the nanoparticles through the deep tissue, 100 micrometer. So we can see the nanoparticles, and using confocal, you will see the one particle, but if we turn on the superrise, it's actually 2 nanoparticle. So, and if we test out, and actually for the first time, we achieved like through the 100 micrometer tissue, we can maintain the 50 nanometer resolution. So on top of this work, we also try to like, because previously we solved the absorption problem, we also try to solve the scattering problem if you want to go to even deeper. So to do this one, we're using a Basel beam. So Basel beam is so-called non-diffracted beam, like based on the interference of the different direction of the beam. So if you have some particle block certain part of the beam, doesn't really matter because the rest of the beam will still have the interference in the focus. So if we combine this Basel beam with our donut beam, we have the Basel algae beam. So you will see if we put a scatter somewhere, we still have nice focus. And if we use this technology, shining on the organoid, actually we can detect each of single nanoparticles, nanomedicines inside this organoid. So this is really important because this organoid is so-called mimic organ. If we study, if we're able to study the nanomedicine distribution on this one, we can directly test for different medicine for the human organ. So we also try to increase the image quality. If we use a one donut beam scanning, like the pink line, actually in the spatial frequency domain, there are some frequency missing, and this frequency missing will induce some like aberration or the distortion of the image for certain frequency. But if you look at the Gaussian, actually it's covered this low frequency range. So for other people, they usually scan the image twice and then do the process to solve the problem. But for us, we actually could use the different response for different energy level. What I mean is like if you use a donut beam to the scanning, depends on different response. The 800 nanometer actually can give you a Gaussian point image output, and the 740 give you a donut point right function come out. And then you can do the Fourier transfer and put these two information together and then transfer again. Then you have a really nice image come out. So we have been using this one to resolve like a really complex pattern like this panda. Because the time issue, I won't introduce this two work, but I want to show you that we also can combine the nonlinearity with the nonlinear SIM to generate some like a really fast deep tissue super resolution imaging. So that is about the superrise, and I'm gonna mention something about the single optical tweezer. So optical tweezers technology to trap single nanoparticles. So for example, this one just 50 nanometer nanoparticle. So it's got a 2018 Nobel Prize because it's really useful for the biological force study. So if you trap one particle, it means like you pretty much confine it inside the potential well, and you move the potential well, move it. But the challenge for this field is like if you want to trap something, you have to have the refract index mismatch because it's based on momentum change. So you can think if you have something really transparent, like this jellyfish inside the water, you don't have so much interaction between the light and your tissue, and then you don't have much force generation. So therefore, for some low index material like nanoparticle and also even quantum dot and some bioparticle, they have really small trap stiffness, trapping force, and also they have less scattering, so hard to be detected. Only gold particle is the popular one. So currently we developed one imaging-based technology to detect the 3D position, get the trap stiffness, and we actually can go to the equinewton force. And using this one, for the first time, detect the 3-dimensional force for the upcoming nanoparticle. And we found that if we dope lots of lanthanide ions, ytterbium inside the nanoparticle, we can increase the suspectivity and the permittivity. And this gave an increased trapping force, and actually 30 times than the convention than the current golden nanoparticle. So it's a huge improvement. And we actually can trap single nanoparticles, see the interaction between the cell and the nanoparticle. We could also like use the particle just like a force dye dress up in a single cell or inside structure to increase the interaction between the light and also the biological tissue. So I'm gonna spend a tiny bit time on single particle tracking. So previously I already developed one method to put a nanoparticle inside the given cell, tracking the position, and then we can have, because we know the size of nanoparticle, we can also map out the viscosity. But the challenge is, if you look at this video, it's hard to get the three, like the XY, the XY direction is high resolution, but in the XL direction, it's hard to get the nanoscale sensing resolution. So we try to solve this problem by introduce a mirror. So if we put an emitter on top of a mirror, actually the emission from the emitter and the reflected one will have some interference. We call it self-interference. And actually for different direction of dipole, this emission, this interference is going to be different because different phase. And interestingly, because for different distance phase different, if you change the position of the particle with respect to the mirror surface, the emission pattern going to be changed from Gaussian to a donut and then to a target. And if you put those particles on different surface, actually you can do some distance sensing. For example, this one, this figure D, you can see that even 10 nanometer difference, you will see the size change from like a Gaussian to a donut. And we compare with AFM, it's really accurate. So we can do this tracking. And most importantly, if we just put a nanoparticle or various different size directly on the surface, you can immediately start checking out like what's the different size. And this method also not affected by the stage drift because it's only in relation to the distance between the emitter and the mirror. So this is pretty much I want to introduce today. So optical tweezer, super resolution, and single particle tracking. So I want to thank my group member. They actually did the hard work for this one. And also I want to thank my collaborator, especially Professor Dang Jin, and also Peter Reis and Dish. So thanks for your attention. And yeah, that's the question part.
Okay, perfect timing. More questions?
I'll ask a quick question.
Yeah.
Regarding the super resolution imaging, when you use a donut beam to suppress the peripheral and a Gaussian beam to image in the center, how does the resolution in the Z direction look like? Basically, how's the focal depth of these two beams?
Yeah. It's a really nice question.
Does that work?
Yeah, because limited time, I didn't include this part. So I guess for different, so for stat, for conventional stat, you can generate a 3D stat because this donut can be like 3-dimensional. So I'm not sure, can you, whether you can see my video. So actually the donut not in 2D, you can, if we just put in like a ring-like face structure, you can make a 3D donut. And then all the how to say, it's just like a bowl and in the middle is empty. So then this entire structure can be depleted. Yeah, and for this technology, we can also do this one. But for my one, this one, we also can generate this kind of structure, but actually we didn't do that. We try to, for this work, the ZX direction resolution is still like just a half micrometer. So diffraction limited, but in the future work, we will try to use multi-beam, like from other direction to improve the XL resolution. Yeah, but for the conventional stat, actually you just generate a 3-dimensional donut. It should be okay. Yeah.
Okay, thanks.
So this is a very interesting way of introducing, I'll say, like a near-infrared labels. I'm wondering, you know, could you comment right, of how you know, this what is the, you know, I'll say delivery method, for example, for particles, and what are the potential towards a label-free or say reducing the use of biomarkers in this case?
You mentioned that how can we use the existing superride to make some label-free superride, right?
Yeah, in particular for the IR window.
Okay, yeah. So for specifically my work, because it's using upmotion nanoparticles, so if you want to image some biological sample, you need to use this nanoparticle to label the single cell. And also for this why when I demonstrate some of this kind of, let me go to the organelle part. Actually, we just use that one to do the super resolution mapping. Where it is? Oh, yeah. Just to do the super resolution mapping of nanoparticles. But in another word, it's like still needed to label. But there are some other technology. So for example, if you just using because the super resolution imaging is based on the frequency domain shift. It's like if you increase, so over here. So if you increase this spatial frequency, you actually increase your resolution. And so there's another technology. You just push the wave vector further, and this is kind of the name is of a spatial frequency shift technology. For that one, you do not need to do the labeling. You just watching the scattered beam, and then you have like a super resolution imaging. So that is label-free one. And yeah, and there are also some work in relation to the super red Raman spectroscopy. So that is also label-free, because if you play with different wavelengths probe, and you can also like try to use the Donald beam and the Gaussian beam, try to increase spatial frequency. Yeah. But for specifically for my work, it's basically using the nanoparticle, so we couldn't make it label-free. But if we just use another technology, it is able to do that. Yeah.
Okay, great. So time's up, and then it's time to wrap up today. And thank you so much, Fan, and to the audience out there. Thank you so much for being with us for 4 long hours. And please come back and join us tomorrow again at the same time. We are having 9 more amazing speakers tomorrow again. So, okay, so that's it, and see you tomorrow. Bye-bye, everybody.
Tomorrow.